Todo lo que
Pánico
digamos
escénico.
queda registrado.
No es para tanto, no es para tanto. O sea,
A
que
mí me
quede
está pasando,
registrado, que quede registrado el diálogo, la amistad,
Sí.
me
¿no?
está pasando que estoy
La
grabando mis
candidez.
clases. Estoy
La
grabando mis
cantidad.
clases y después las subo a YouTube para que los estudiantes las puedan ver. O sea, doy las clases en vivo y después las subo a YouTube. Y cuando las subo a YouTube, la verdad es que nunca las miro, porque si las
Es
miro,
terrible.
decido
Es
no
terrible.
subirlas, claro. O sea, todas las cosas que normalmente serían olvidadas por un,
Claro,
un
quedan
manto de
ahí.
olvido, claro, que serían cubiertas por un manto de olvido.
¿Alguien podría checar
Diego,
si es que estamos se
¿Qué haces,
supone,
hola
Diego?
Diego, ¿qué
oh,
tal?
Hola a todos.
hola a todos.
Bienvenido.
Eh,
Gracias.
¿Alguien podría checar si ya estamos streaming de verdad? Yo creo que sí, porque ella me dice que
Ah,
ya estoy live.
a sí, ver. Aquí mismo incluso se puede.
Y
Eso nos dice. Acá, sí.
se supone que hay 7 personas mirando.
Sí, ya estamos.
Ahí está Olivera, ¿eh?
Sí, ya
Hola a
estamos.
todos.
Bienvenido.
Ok,
Vale.
entonces ya,
Vale. Hola, hola. Llegó nuestra chair.
llegó nuestro chair, pero entonces,
Hola, Olivera. Sí.
Hola.
¿alguien podría checar si ya estamos streaming de
Sí.
verdad? Yo creo que sí, porque ella me dice que ya estoy.
Hello.
Ya. Pero ahora hay
Hey.
que,
Hello,
ese
Olivera.
ya, córtalo, porque hay el feedback. Hola,
How are
Olivera.
you?
Hi.
Quien
Fine,
sea que
fine.
estaba escuchando el streaming, por favor.
Pedro.
¿Ya, Tomás? ¿Tomás eras tú?
Lo apagué, sí.
Ya,
Cuando
ok,
la gente llama a
gracias.
un programa de radio y deja la radio encendida.
Sí.
Sí.
Ah,
So
hay
now
algo en el
we-
chat. ¿Quién está viendo el chat? Hay algo en el chat.
A ver, Online. Miguel Ángel Martín dice que estamos online.
sí.
Ah, ok.
Gracias, gracias.
So now we switch to English, I think.
Ok. A cambiar el chip.
Yeah, now it's official. Let's do it.
Let's do it. Let's do it. Okay. And well, so we're waiting for our speaker, and as soon as he arrives, I'll make him co-host, and then we'll be good to go. Did he say at what time he was going to show up?
No,
And,
shouldn't be long, I suppose.
Okay. I'm going to raise my desk.
Wait, what? Is it
that's
automatic?
it's high technology.
Okay.
Can we raise mine as well, please?
Not yet. Okay, cool. Un poquito más.
Let me test this music for for
The
chairman
time.
Yeah.
Yeah,
Yes.
Olivera, please do.
to see if you hear. Just a moment.
That's a good idea. That's Guille,
Yes.
right?
Do you hear it?
Yeah.
Okay.
Probably a bit closer or a bit louder would be
Okay. I
more
will.
noticeable.
Let me put it louder then.
What is the raise the hand feature of this?
You go to participants and
participants.
Click
next
the
to,
participant.
on the left of the, there's a check mark and a cross and so on. At the bottom of the list.
Okay.
Okay, raise your hand, Nico.
¿Hay algo más en el
Sí,
chat?
the
¿Quién
words.
está viendo?
Ahí está.
Sorry. Who's looking at
Yeah?
the chat?
Okay, perfect.
I'm looking at the chat.
It's
Okay.
Rodrigo Lea just saying hi.
Put my hand
Okay.
down. Okay.
Makes me anxious because I see the chat.
Yes.
and it's
Let
like-
me see also where is this participants. So I have to open.
Yeah,
Yes,
so you open the
okay.
participant sidebar and
Yes,
then,
yes, I see. Can somebody
then-
raise the hand to be?
Yeah.
I am trying now.
There you are.
Okay. So
And
it
then-
appears in the order. Okay.
Yeah, that's nice.
And-
Yeah, exactly.
And who will remove? Okay, good.
I will remove them. I will lower
Perfect.
them.
Okay, now now it is louder. Can you listen if you hear well?
Yeah, it's good.
Yeah.
Yeah, that's good.
Okay,
Thank you.
Perfect.
fine.
So Guille has a question apparently. Hola Guille.
Hola, ¿cómo andan? ¿Por qué hablan en inglés si Olivera entiende perfecto castellano? ¿O hay alguna
It is not because of me.
Dijo que
No,
no.
just kidding,
It
really.
is not my
Hablamos
fault.
en español.
No vengas a
No
desordenar.
es mi
Guille.
culpa.
¿Cómo andan?
Bien, ¿y tú, Guille, qué tal?
Guille.
Acá, muy bien, contento de verlos a todos, la verdad.
Sí, sí, sí,
Lo
la
mismo.
verdad que es bonito verlos a todos.
Así
Y-
que bueno, che, le estaban explicando a Olivera lo que todos tenemos que hacer durante estos días y yo ya llegué tarde.
A mí me quedó
Ya.
una pregunta, ¿cómo hago para bajar? O sea, yo sé que yo levanto la mano y la puedo bajar, pero cuando sea host, ¿cómo hago para
No,
darle down?
no te preocupes de eso, yo la bajo.
Ah,
Yo,
bien.
yo voy cambiando la lista, sí.
It's like playing whack-a-mole.
Okay, Anderson is here. So Anderson, you're here, right? So I will make you a co-host, not make host. Anderson, where did you go? Anderson, could you say something, please?
There's our speaker.
Not yet.
Yep, I just let him in.
Ah, okay.
Hola, Juan.
Las instrucciones que mandaron son dignas de una persona muy obsesiva. No
Ajá.
voy a preguntar quién las escribió.
Who could that be?
Only 21 points to be chairman. This is nothing.
Hola,
Hola.
Juan.
Hola, no sé si me ven. Hola.
No te
No.
veo.
Ah, no sé cómo
¿Dónde
hacer.
está?
Soy Martín Schrödinger. Buen día.
Hola Martínez, no te
¿Cómo andan?
vemos.
Yo los veo a todos, pero no puedo hacer que mi cámara ande.
Pero,
Elena, is Juan a co-host already?
Yeah, give me a second. I'm trying to find him, and if nobody says anything for a second, I will manage to
Bueno,
do it. Because
I can speak now, so
yeah,
yeah.
okay.
You
Hold on a
find me
second.
now?
Hold on a second. Hold on a second. Yes. Now you're a co-host.
Right. Okay.
Yeah. It's just that when somebody talks, so I have my cursor say on somebody's name, and when somebody talks, the name shifts.
Oh, I see.
So I'm kind of end up making co-host somebody else. Okay, but now you're a co-host, so you should be able to share your screen and everything.
So in principle, you could start, I think, no?
Here it says that there are people in the waiting room, so
Yeah, no,
Yeah, we are.
we'll let them then. Yeah, we'll let them in as they arrive.
so someone else is admitting people?
Yes.
Yeah.
Okay, good.
Yes.
Don't worry about that.
Uh-huh.
So then I will go ahead and start. So I'm just going to say a couple of things, and then after that I'll hand it over to Olivera, who's chairing the first session. Okay.
Okay.
So we start.
Yeah.
Yes.
Yep.
Yes.
Okay. So
Go for it.
share my screen. Okay. Okay, so welcome everybody to LAWGH. This is the second Latin American workshop in gravity and holography. And LAWGH is really the biennial meeting of the Siembra Holograph Network. This network gathers professors and postdocs from Latin America or from any nationality working in Latin America who do research in holography and gravity. In 2018, we were approximately 140 plus students. So we're really a very large group. And our goal is really to strengthen the sense of community, foster scientific collaboration, support emerging groups working in this area, and contribute to the training of future researchers. So in other words, we just want to do physics and have fun and be useful in some way or another. So as I said, this is the biennial meeting of the network, but we have never hosted a 100% virtual meeting. So there might be some hiccups along the way, but the whole point of LAWGH and of Siembra is that we're all friends. So we're counting on your understanding. Let me, with that, go over a few logistical points. Some tips for participants. Please leave your mic muted and camera off when you're not speaking. Use the raise hand feature to ask questions. When you are called to ask your question, if you can introduce yourself and then turn on the camera, that's great, so the speaker can see you. Otherwise, whatever, just say your question. During the talk, you can post questions in the Zoom chat. Every day, we will have a discussion session at the end of the day. So if there were some questions that were not answered during the talks, then we can revisit them in the discussion session. And because of this virtual format, we decided that the applause thing is a bit awkward. So we decided to just forgo the applause and just applaud with the clapping icon. I hope that's okay with the speakers. And now for the speakers, tips for the speakers. Remember that faculty and postdoc talks are 30 minutes plus 10 minutes questions. Students' talks are 20 plus 5. You will show your slides using the share screen thingy in Zoom. And the chair will let you know when you have 5 minutes left. If everything goes well, you will hear a chime. If things goes wrong, then the chair will find a way to let you know, but they will let you know when you have 5 minutes left. And it's important to stick to the times because we have a 5-minute break in between talks. And I think that's really important to have those breaks in between talks to kind of keep us sane. And with all that, this is how our week will look like. So we are here and every day we will have a discussion session. And on Wednesday, we have a gender panel. And on Thursday, we have a conversation about the holograph network. So ideas for the future, what to do, et cetera, et cetera, et cetera. So I think that's it from my part. So welcome to LAWGH. I will stop sharing my screen and hand it over to Olivera.
Morning, everyone. I have pleasure to introduce our first talk for this conference. That is Juan Maldacena from Institute for Advanced Study, and he will tell us about cosmological wormholes.
Okay,
so
thank you.
I invite the speaker to share the screen.
Okay, let me share the screen. Second. Okay, can you see the screen? Can you hear me?
Yeah.
Yes.
Okay. Okay, so I'll be talking, well, first of all, thank you for the invitation and thanks for organizing this workshop. And I'll be talking about ongoing work with Jimin Chen and Viktor Gorbenko, which should appear soon. So the idea is that we will compute some fine-grained entropies using the Ryuta-Kanagi formula and its generalizations with the goal of getting some insights on cosmological questions. And this will lead us to some interesting sort of bracket wormholes or cosmological wormholes that I'll try to explain what they are. And we'll work in mostly in 2 dimensions. I'm having trouble. Okay. So the general philosophy is that we will use this gravitational fine-grained entropy formula, which is the Ryuta-Kanagi formula and its generalizations. And what this formula allows us to do is it gives us the entropy of the exact state produced by a certain gravitational path integral in terms of properties of the semi-classical state. So on the left-hand side of the formula, we have the entropy of some hypothetical exact computation in quantum gravity theory. And that entropy is approximately given by this formula, which is something that we can calculate purely in the semi-classical state. So here we have the semi-classical state. We mean just the state that is produced by classical geometry and quantum fields propagating on that classical geometry. And then we have to calculate the entropy in some regions at the area, extremize, minimize, etc. So this formula is best applied when there is a region where gravity is not important. So for example, ADS and its boundary. So when at the boundary we don't have gravity, or we have it, let's say ADS coupled to flat space with no gravity in that flat space region. So as a simple sort of cosmological toy model that we'll have in mind, we have something like this. So we have a period of something like the zeta revolution with dynamical gravity. And then in the infinite future, we switch on to a flat space evolution with no gravity. Okay. Of course, here we could take a slice very late in time and then join that to flat space and then take that limit to infinity. And we consider quantum fields propagating on this geometry. So we imagine the zeta gravity with a conformal field theory. And then we have the same conformal field theory in the flat space region. And the conformal field theory just passes through this switch in behavior of the metric with no problem, because here the metrics are both conformally flat. Now we'll mostly consider this in 2 dimensions. And so we'll consider JT gravity in this region plus a conformal field theory. And then here we have exactly the same conformal field theory. So that's the main model we have in mind. You can view this as a model for inflation, where we have inflation here over some time, and then we have some kind of reheating, and then we have a region where the universe is not expanding very much, and we approximate that expansion as being completely, as there being no expansion, and also as the dilaton or the gravitational strength of the coupling being very, very weak in this region. Okay, so that's the basic setup. But first we'll take a long detour, which itself will have, and we'll end up having some interesting sort of cosmological space-time in it. This detour involves first recalling a certain black hole toy model that is very similar to what we just discussed. And this consists of ADS2 with gravity plus a conformal field theory, and then flat space with no gravity plus the same conformal field theory. So here we have an ADS theory, and then the conformal fields can leak into some flat space region. And we put here transparent boundary conditions for the conformal field theory. This is a model which was used to great success here in this paper to calculate properties of black holes. But of course, it goes back to early models of black holes. Now, this gravitational region, we can think by holography, we can replace it by a quantum mechanical model that lives purely at the boundary of this flat space region. So from this point of view, we have a CFT with a boundary. And this can model certain near extremal 4D black holes. So now we'll discuss a very closely related toy model, which is basically the same as that one. But we first go to Euclidean time, and then we rotate, we exchange Euclidean time with space. So of course that in Euclidean space makes no difference, but it will make some difference in the physical interpretation of the model. So we imagine now here we have Euclidean ADS, or also called hyperbolic space, and with dynamical gravity. And then here we imagine this as preparing a wave function. And then we evolve that wave function using flat space gravity here. So that's equivalent to starting with a boundary state here and then evolving that boundary state in time. This is a boundary state in a conformal field theory. The boundary state, if we are doing JT gravity here, is not quite conformal invariant, but we can certainly consider non-conformal invariant boundary states. And so we imagine, so this produces a boundary state B, and then we evolve some Euclidean time tau. We'll get some state here, and that state then can be evolved in Lorentzian time or not, as we wish. So first we'll study this Euclidean model, and it's simpler than the DS model, but there's also cosmological interpretation that has many of the same features. So in order to understand features of this state, it's useful to consider entropies of intervals, such as this interval. And the entropy of this interval, so the naive semi-classical entropy would be just notice that the fields live in a conformally flat space. So we just have the ordinary vacuum for the CFT here, and the entropy of the ordinary vacuum from an interval is this expression. Now, when this expression has the feature that when L becomes very large, when L becomes very large, the entropy becomes very big. That reflects the long-range entanglement of the vacuum. However, from this kind of boundary interpretation, we expect that the entropy should be finite at very long distances, because the amount of entanglement that can be transferred by this quantum mechanical system that lives here is just basically given by essentially S0, and so we expect at most one factor of S0 from each endpoint of the interval. That's connected when we rotate time and space to the fact that the black hole has finite entropy. So when A is very large, in principle, we have a cut here, but we could, of course, move the cut here. And then when it's in the gravity region, we know that it can split into, and we pay here a price of the value of the dilaton here. So now this is, we have some kind of island here in the middle. And now we can consider the entropy, basically, of these regions and add the surface here. So that's essentially this expression. And when these two regions are very far from each other, when the A is very large, we can just have the sum of each of these two factors. And that reduces to entropies of an interval. And sort of for each problem, by symmetry, we expect that the extremal surface will be located well, at the same x position, at the same horizontal position. And then in the vertical position, which was Euclidean time, we just have to, well, we have the expression for the dilaton, which is a constant part plus the varying part of 3t gravity. And then we have just the usual entropy of an interval, just rescaled by some factors and so on. So we extremize over C, and then we find the value of C. So we find some particular position here, and we find some entropy, which, so for large enough L, this dominates. I think I'm missing, unfortunately, one transparency where I gave the, well, there is some entropy that we find here. And the entropy that we find after expressing, putting in this factor of C star, ends up being an entropy of order 2s0. Okay, 2s0 plus some plus C, something of order C. So the point is that we got the result we expected, that the entropy would be finite. Okay. And for large enough L, this is what dominates, because this will have lower entropy than the entropy of the interval. And so more technically, we worked in some approximation where we neglected some things. So for example, the quantum mechanics of the graviton. I will not go through this in detail, but so we scale the parameters in such a way that the calculation boils down to what I told you, and we can neglect other effects. Okay. So in this computation, actually, there are various minima. So there could be that this point could be on this side. So in reality, there is a bra part of the state, and then there is a cut, and then we are tracing over the outside. So we're connecting them here. So this is standard when we calculate the traces, well, compute the entropy by the replica trick, but this is something that is involved also in calculating the density matrix for the interval. And then in the end, these extremal surfaces could be either on the bra side of the diagram or on the cut. So there's a kind of C2 symmetry breaking. And in principle, we have to sum over them, but those give subleading contributions. So this result looks qualitatively reasonable. It is saying that the entropy of the interval cannot be bigger than 2s0. It's roughly what we expect for a state with a bounded long-range entanglement. So that's pretty nice. However, these results are wrong in detail. So the entropy obtained in this way does not obey the strong pseudo-additivity condition for certain choices of regions. And we really got to this by, so I'll explain in detail what these regions are. But before we got into the details, we really got to this by thinking about the de Sitter problem and trying to figure out where the entanglement wedge was and so on. And by that, we ran into a contradiction there, and then we realized the same contradiction was present in this model, this simpler model. So this strong additivity paradox consists in taking three regions, and well, the strong additivity is some relation between various subsets of the three regions. So you can consider region one at a time, or maybe three regions together, and then pairs of regions. So that's the nature of the strong additivity condition. And here in the flat space region, we can pick the regions as follows. So first, the matter field, we think of it as a sum of two separate matter theories. And here in the flat space region, those matter theories are completely non-interacting. However, and because they are non-interacting, and because they are non-interacting, we can consider the same interval, but consider either one of the matter theories or the other matter theory. Okay, or one of the pieces of the matter. So the matter theory is the sum of some red fields which have a central charge much bigger than 1, and then one extra matter field here in blue, which has only one field. And in this region, they're completely non-interacting, so we can separately consider the interval A, which is just this interval, but with only the red fields, or the interval B, which contains only the single extra field, or the union of the two, which appears, for example, here, which contains both of them. So in that case, if we had the union, we would get the result we had before. And anyway, so I won't discuss in great detail the paradox, but when you consider this setup, you find that, well, maybe I should, yeah, the key point in the paradox arises because when we consider the union of A, B, and the complement of B, so the complement of B is that single field, but only outside. So we consider B and the complement, we have a pure state for the field B. And then we are just considering the same cut for the field A's that we had before. And when we bring it down here, this emerging surface will create a cut both for the field A and the field B. But the field B has no cut because we're considering the full interval. So we end up with a cut going between these two quantum extremal surfaces for the field B, and that produces this extra log L. Actually, there is a mistake here. There shouldn't be this factor of C. It's just only one field. But the important point is that it grows with L. And so we can make this right-hand side much bigger than the left-hand side. And then there are some terms that cancel between left and right-hand sides. Anyway, so there is some problem with this. And the way, so if it is wrong, why are we talking about it? And the reason we are talking about it is that it's just to show that the previous discussion was incomplete and there is something wrong with that view of the state. And so there is some new idea, and the new idea is that we should consider new contributions to the density matrix, which we'll call bracket wormholes. So the idea is the same as before. So here we've drawn the interval, and then there is a bra evolution here preparing the state, and then there is a ket evolution preparing the ket part of the state. And the idea is that the two are connected here in the past, if you wish, or the Euclidean past, so they're connected. And so when we consider, for example, the trace of the density matrix, we have a contribution which is essentially a cylinder. Okay. And the cylinder can be viewed as essentially the same as the eternally traversable wormhole that we discussed with LAWGH, but which in turn was based on the traversable wormhole of Gauss, Jeffreys, and Wald. And here the idea is simply that we have a theory which, so the green region looks basically like Euclidean ADS2 in global coordinates. And then, so this, well, perhaps I should say it slightly differently. So if you imagine the holographic interpretation, we have one quantum mechanical system here on the bottom part and one quantum mechanical system on the top part. And this Euclidean evolution yellow is connecting the two. And so now we have two interacting quantum mechanical systems. And it is conceivable that the gravity dual of that would be connected and would have a geometry where the two sides are connected. Certainly not obviously in contradiction with holography, because we're connecting the two sides. And so, and indeed, one can find a solution of this kind. So this is an actual solution of the equations, and there's a precise form for the metric and the dilaton of the solutions. Okay. Now, the metric is just the standard metric in Euclidean ADS2 in some sort of stripped coordinates. So here sigma goes between minus pi over 2 and pi over 2. So sigma equal to 0 is here the center where the warp factor has the smallest value. Then it grows towards the two boundaries, so this boundary and the bottom boundary here. And then the dilaton also grows as you approach the two boundaries. So this is a symmetric function. So now it's interesting that this geometry also has a Lorentzian interpretation. So we can cut the geometry at this point. So this is a point of time reflection symmetry. And at the same time, we cut it on the other side of the cylinder. So we get two disconnected universes, one yellow universe without gravity, and a green universe with gravity. Okay, and the quantum fields in this setup will look thermal. So on both the yellow region and the green slice in the back, the state looks thermal simply because it was prepared by this. We had a Euclidean time, which is a circle, so we'll have some effective temperature. Okay, in the limit that this yellow interval is very small, this effective temperature is set by the coupling constant that appears in the Schwarzian theory, in the JT gravity theory. Okay, so now naively it looks as if we got the thermal state here, and on the other hand, from the holographic interpretation where we thought that we had a pure state that was evolving, we should have had a pure state. Okay, so we'll solve this problem in a second. So the Lorentzian continuation, if we draw it for the case that the circle is compact, so here I'm imagining that the horizontal direction we compactify on a very big circle of length L. This is not crucial, but makes this picture a little more clear. So if we have a compact circle here, and so we have a cylinder, and then we have the Euclidean evolution with Lorentzian cylinder here from this time onwards. And in the past, we have the Euclidean evolution up to the time where we join to the curved space geometry, and that then is connected. This was the slice at sigma equal to 0. And if we continue that slice in Lorentzian signature, we get an FRW cosmology with a collapsing universe. Okay, so it's a closed universe that collapses. So this is another diagram of the same thing. So on the Lorentzian continuation, we can continue both forwards in Lorentzian time and backwards in Lorentzian time. So we have here a thermal state on the cylinder, and we also have a thermal state in this closed universe that collapses into singularity. And this is a singularity just both geometrically in the case that the circle shrinks, but also the dilaton goes to strong coupling in this region, so it goes to minus infinity. And now the state, it's a thermal state here, but the state is entangled between these two sides. So we have the matter state is roughly in the thermofield double of this conformal field theory. So one side of thermofield double is this, and this is the other side. So together they're in a pure state. And so if we looked at the full entropy of the universe here, naively we would say it's thermal, but if we include this closed universe as an island, as the RT formula instructs us to do, we find that if we include now both of them, we get a pure state, we get zero entropy. And in particular, this is also saying that the so-called entanglement wedge of the cylinder includes also this closed universe. And so the general belief is that, so it's a conjecture saying that if you, everything that is included in the entanglement wedge is basically accessible to arbitrarily complex operations that you do, for in this case on this state. So I like to say that this is a kind of puppet universe, this one here. I mean, this is just some poetic analogy where the threads of entanglement that join the state in this universe to the state here somehow allow you to read off what is in the closed universe and in some sense control it by doing complicated operations here. Now this new so if now you wanted to do the entropy of not the whole universe by just some interval, then for a very long interval, let's take L now to be very long or infinite, and then we have a very long interval A, and then the island in this case will be on the other side here of the universe. And in this case, we don't run into any contradiction because of the following. So at this had a time reflection symmetry at sigma equal to 0. And then it turns out that the entropy subadditivity inequality that we had before reduces to a similar entropy subadditivity inequality just for the bulk quantum fields. So the bunch of area terms that cancel, and then we would have the entropy additivity quantity for the bulk quantum fields. But for the bulk quantum fields, the state that when we cut it here at sigma equal to 0, both in the back and the front of the cylinder, is a perfectly reasonable Lorentzian state. So it will obey the additivity condition. Okay, so the conclusions of this part of the discussion are that we consider the gravity dual of a particular non-conformal boundary state of a CFT. And for large circles, it produces a state which can be interpreted as coming from a bracket wormhole. In the semi-classical description, we have a thermal state on the circle in the CFT, which is entangled with a closed FRW universe. So the closed universe cosmology is in the entanglement wedge of the full state of the CFT. And so in this way, you can say that you are giving a holographic description of a cosmology. In the sense that we can describe this closed universe as being part of a very complex state in a CFT. Now, this is really very analogous to a black hole that forms and evaporates. So when we have a black hole that forms and evaporates completely, then the entanglement wedge of the radiation includes the whole black hole interior. And not only that, but inside the black hole, we have a kind of collapsing universe, or collapsing interior. And that interior is entangled with the outside radiation. So it's very similar to what we are discussing here. The only difference is perhaps that in our discussion here, we have a complete U1, a complete symmetry. I mean, it's more like an ordinary Friedman universe where we have a translation symmetry on the circle. I should say that this construction that we discussed here relied quite a bit on being in 2 dimensions, because those kinds of bracket wormholes in Euclidean space, they exist relatively easily in 2 dimensions, but it's higher. They seem more difficult to construct in higher dimensions. I mean, in a higher dimensional ADS context. Of course, if you have a higher dimensional ADS where there is some region where the space looks like ADS2, then that's easy again. It's just difficult to make them with the full, okay, so now we move to the case of the sitter, and the short story is that something similar happens, and there are several caveats in the word similar, and the final picture, I should say, it's a bit strange. So you're entitled to think that there is something wrong in what I'm going to tell you, but we try to find it and find it. So maybe you will be able to find what is wrong. So we go back to the simple cosmological toy model that we discussed in the beginning. This is a kind of motivation, and we'll then we can now do exactly the same calculation we did before. We consider the interval, and again, the standard Bunch-Davies vacuum or Hadl-Hawking vacuum of the sitter plus then this flat space evolution. Because the metric is conformally flat, that will be the usual vacuum in Minkowski space. So the entropy of A is given by this. So that's the naive answer. Now we can look for these island-like computations. And indeed, there are such islands. And we get essentially the same case as in the Euclidean ADS case. So again, there is a region that minimizes the generalized entropy and so on. Now, there are a couple of differences. So, well, there's one difference basically is that these 2 insertions, so I mean, once we do the replica trick, there is secretly a twist operator inserted here, another one inserted here. But now this vertical direction is a time-like direction. Because of that, we are computing a 2-point function of 2 points that are 2 twist operators that are time-like separated. And this, when you go through the motions of the replica trick, implies that there are some i's in the entropy, in the contributions to the entropy when we compute this particular contribution. But those i's somehow cancel out when you consider the contribution from the bra and the cat. I mean, the computation in terms of twist operators is manifestly real. It's a manifestly expectation value permission operator. So it really gives you a real answer in the end. But it's a situation where some pieces, some intermediate parts look a little funny. But regardless of that, which seems to be a kind of more technical point, we still have the same entropy subadditivity paradox. Now here we can now ask whether again there are some kind of bracket wormholes, and when the space direction is very large, and well, in general, even if it is compact, it seems that a good candidate for a bracket wormhole is one based on this geometry. So this geometry is roughly the geometry of the Sitter space. Well, it's not roughly, it's exactly the geometry of the Sitter space in so-called Milne coordinates. They have the feature that there is a singularity at tau equal to 0. Well, it's not really singularity, it's a coordinate singularity at tau equal to 0. But we could make X compact and then it would be a real singularity. But the idea is that in order to construct this wormhole, we are going to make use of the fact that we can do some Euclidean evolution. So normally when we construct the Hartle-Hawking state, we do some Euclidean evolution. And so we'll do some Euclidean evolution, and the Euclidean evolution will consist in moving around tau equal to 0 in the Euclidean direction, complex tau direction. And it boils down that when you go to conformal coordinates, so we pull out this factor of sinh squared and define conformal time, this little portion of the circle amounts to moving eta by I pi. So it amounts to a Euclidean time translation in eta. So it's a reasonable thing, and it has this, this topology. And now we think of this part of the geometry, which if one were naive, one would consider that to be the past region of this Milne wedge. We consider that as being part of the bra. So this is the ket of the state, and this part here, we think of it as being the bra. So it's like we're identifying this point with the point here. So this geometry is very similar in spirit to the so-called double cone that Saad, Schenker, and Stanford used to discuss the ramp behavior when you consider the long time correlators in a black hole background. So the difference with their story is that now this direction is Lorentzian, so this tau direction is Lorentzian, so we basically exchange space and time in their calculation. Now, when you actually compute the value of the action of this type of configuration, so what I discussed so far is somehow roughly the off-shell configuration, the geometry itself. But when you actually compute the action, because in JT gravity, phi multiplies r plus 2, or r minus 2 in this case, and r minus 2 is 0 in the bulk. So in the bulk of the space, we get 0 action in the whole bulk. So we get only a boundary contribution. And the boundary contribution is the complex conjugate on the bra side and the ket side. So in the end, the gravitational piece gives us 0. So it cancels completely between the bra and the ket. The quantum field theory piece gives some contribution, which is proportional to L and the central charge, and some effective temperature. So effective temperature is roughly it's related roughly to the length of the wormhole. So the whole geometry has a free parameter, which is roughly the length of this region. And that free parameter sets this effective temperature. So we can think of the effective temperature. So effective temperature is just the temperature of the quantum fields we would see here in the yellow region. Okay, and so that's a free parameter. And it turns out that if you evaluate the action in this way, this free parameter is driven to infinity. Okay, so that's the answer we get, and I promised that it would be a strange answer, and we think that this is the right answer for this system. Now, large effective temperature means that this is a kind of short wormhole, and it also means that there is a short period of inflation. So you can think of this setup in the Milne coordinates that you create. Well, I'm running out of time, but well, maybe I should say So you, for tau close to 1, so you created this Milnor region, can be viewed as, if you wish, as a bubble nucleation, or maybe create, yeah. And then that expands over exponentially, so in an inflationary way, over some time up to some cutoff. So in the limit that this goes to infinity, it's infinite time, but we could regulate it, and then there is some finite time. Then this free parameter we are talking about would let you vary the length of inflation, and we sort of prefer the short period of inflation. And this is similar to problems that arise in the usual Hartle-Hawking wave function applied to inflation. So one strategy would be to say, oh, well, we should never apply the Hartle-Hawking wave function, and we are just finding problems that that arise because of trying to apply the Hartle-Hawking wave function. The right wave function of the universe should be viewed, should be found in some other way. But you know, so here our task was to compute it for this case, and well, this is what we got, it gives a strange answer. Now, I have not much more to say about this. This funny thing, but this is what this setup gives. It might be that just shows that this setup will not be useful for describing our universe, which was never intended to be, because it was two-dimensional, but even the most basic feature of producing a state with not infinite temperature is not reproduced by this setup. But I would like to mention that when we compute the wave function of the universe in the Hartle-Hawking philosophy, we normally sum over universes with no boundary. So when we compute the wave function, we sum over all universes with no boundary here. But when we trace over, normally when we compute a cosmological observable, we are tracing over some parts of that we don't observe. So in this case, in this particular setup, we are tracing over some degrees of freedom in the quantum field theory. And either that or tracing over a portion of these slice that we don't see produces some connection between the bra and the cat. And that should tell us that if we are computing, after we do this trace, it's natural to connect the bra and the cat of the state. And so it's natural to search for solutions which contain, where the density matrix of the universe is created by connected geometries. Okay. So this is regardless of whether this density matrix is the ultimate definition or not. Even if this is the left-hand side is the ultimate definition, after we do a partial trace, it's natural then to connect this, to connect them and to look for this type of wormholes. And I've showed you an example of how this wormhole can solve a particular problem, even though they give a, I should have mentioned that even though we get a funny answer, so we could regulate this temperature by adding a little bit of Euclidean evolution, and then we get a well-defined finite temperature, and the problem with the entropy, so the additivity paradox, is gone. And finally, well, maybe I ran out of time, I won't say that. So we have discussed the need to include a bracket wormhole in computing some cosmological observables in the context of some specific toy models. The state continues to be pure, but it looks thermal in the semi-classical gravity. And again, the de Sitter entropy is once you do that, is also the maximal entropy for an interval. Now there are many questions, well, there are many questions. You would like to go from d equal to 2 to d bigger than 2. And in this 2D model, we got an answer which doesn't appear to make phenomenological sense. No one could wonder whether Hartle-Hawking is always doomed to failure, and many people have that opinion. But maybe some other models of gravity give more reasonable answers, or maybe changing the rules slightly will give more reasonable answers. And eventually, if we understood this, perhaps eventually in the far future, we would expect some applications to cosmology. Thank you.
Thank you. We have just a few minutes for 2 minutes, in fact, for the questions. Is there any question? Okay, Andres and Avalon, please. You can turn on your camera and microphone.
Hello. Well, I cannot really turn on my camera, but
it is okay.
Because it says that the administrator stopped my camera, so I cannot turn it on. But well, now I can do it. So, well, nice to see all of you. It's very nice to see so many friendly faces in this Zoom conference. Well, I have a question. There is like a long-standing problem in general relativity, that is to define the energy of the zither. And this is because the zither has no spatial boundary, right? It has compact sections. So, so the boundary terms in general relativity that usually give you the energy are zero.
Right.
So since you can compute the entropy, do you think that this can lead to a definition of the energy of the zither space?
Well, my short answer is I wouldn't expect it to, because I think it's reasonable that there isn't an energy in the zither. Well, normally you need an entropy and a temperature and so on. But here what you compute is the entropy of the whole slice in the future, for example, right? And you get zero, which so it's not very useful. Well, it will give you zero energy if you want, but
okay, thank you.
Sure. Yeah.
Thank you. Next question is by Leopoldo Pando Zayas.
Yeah, thanks for the nice talk. So my question is a little bit basically asking if you could elaborate a little bit more about going to higher dimensions. So let's say we have ADS4 times S7, something well built in a string theory, and we know IBJM theory, we can compute entropy. So what how far do you think one needs to get to understand?
Well, so for what I discussed today, it was crucial to be in 2D and have these conformal fields. So if you have ADS4 cross S7, you could imagine putting a black hole type geometry in ADS4, right? And then in Euclidean space, so for example, you can put a magnetic flux on the S4 on an S3, right?
Yes, S2.
Well, S2 times S1. So you consider the boundary to be S2 times S1. You put a magnetic flux on S2, and then you could fill that in with an extremal or near extremal black hole. Now, then you would have to add something else to produce conformal fields. I'm not sure what that would be in this case of the ABJM theory or some other example. What?
That presumably you're saying will not come directly from M theory, so I have to couple the M theory stories to something else. Is that
well, I mean, we would like to have the conformal fields and have a large number of them. Maybe just by adding an AN singularity, that's enough. So ADS7 times ADS4 times some 7-dimensional space, maybe just ADS7, and then adding some. Maybe that's enough, or maybe one would need a little bit more construction. I don't see anything that should stop it.
Okay. Thank you.
Thank you.
But that's roughly
Okay. We are already in our break session, but I don't want to cut maybe the last question by Carlos Nunez, if it can be short, please.
Okay. So one of the questions I had was taken by Leo, so let me ask the other one. At some point, you discussed two quantum mechanical systems, right, that they were connected, right, by a process that I did not understand which was it. And you said, okay, holographically, these are two ADSs that are connected. So can you explain how these two quantum mechanical systems are connected, how the two ADSs are connected, and what the characteristics are of them?
Yeah, so the idea is that you have this, the holographic description is two quantum mechanical systems that are connected by the Euclidean evolution. Good. So that interpretation is more reasonable if you rotate them and view the vertical direction as time. So then you have quantum mechanical systems connected by that evolution. The dual of that then is you have to in principle, each quantum mechanical system has its own separate gravity. Naively, you would think. Yes. But given that these are two quantum mechanical systems that are connected, it's not a problem to have a single gravity solution. And so you could have a gravity solution which just goes around and gets connected. And that's what we...
What confused me of that, suppose that one of the quantum mechanical systems has lots of degrees of freedom and the other has few degrees of
Oh no, here
central
it's
Clark.
important that the two are identical, that there are two identical quantum mechanical systems.
Okay, so in the dynamics, basically the Lagrange and
Yeah,
everything.
yeah, they have the same Hamiltonian, yeah.
All right.
Yeah, it's important that they're identical. I didn't say that, but yeah, these two boundary states are identical.
Thank you.
Thank you.
Sure.
And finally, the Teramond, the last question for this session.
One very brief question. I was confused in one of the first slides where you wrote the relation between ADS2 and CF2, because in principle, the relation is between the isometries between ADS2, SO21, in fact,
Yes,
also with conformal R1.
yes,
So I was
naively,
confused by this
naively
statement.
one would think ADS2 CFT1, right? But what we have here is ADS2 plus a CFT. So that's the CFT2 was a matter CFT that lived in the space, right? In that two-dimensional space. We are not claiming that the CFT is dual to the ADS2 space.
Okay,
Yeah,
thank
what
you.
is dual to the ADS2 space is some quantum mechanical system that we were talking about a moment ago.
So it's a sort of extension.
Yes.
Okay,
Well,
thank you. Sorry.
Thank you very much. All other questions can be discussed during the discussion session. Now we have a 5 minutes break and we will meet at 11:50. Thank you.
Thank you. Bye-bye.
Bye. Okay, I think we can start with the second talk. Now we will listen to David Berenstein from the University of Santa Barbara, and he will tell us about giant magnons and giant gravitons.
Thank you, Olivera. So I want to tell you about something that used to be very, very popular about 15 years ago. And then while everybody else is talking about entanglement islands, I've gone back to some of these problems. This is based on recent work that I've started with one of my students, LAWGH. But a lot of the stuff we've done dates back to many years ago with previous groups of students. Okay. The basic starting point is the idea of CFD correspondence, also known as the gauge gravity duality. And basically, the idea of CFD correspondence is a realization of holography in terms of a quantum system, which is complete in the sense that we know the UV theory and we can, in principle, do any calculation, although they might be rather complicated. And then the idea of CFD correspondence was discovered by Juan in '97, and it's been more than 20 years since, and we're still working hard at it. So it is a complete equivalence between certain quantum field theories, usually gauge theories, that are similar to a standard model, and quantum gravity theories on spacetimes that have higher dimensions, whose boundary, or more precisely the conformal boundary, is the manifold sigma on which the quantum field theory lives. And then the correspondence requires that the quantum gravity theory have appropriate boundary conditions to match to the quantum field theory. Okay, and the idea is that anything that can happen in quantum gravity can happen in quantum field theory, and anything that can happen in quantum field theory can happen in quantum gravity. The simplest example of the gauge gravity duality is the one that Juan discovered first, which is n = 4 Yang-Mills. That's a 4-dimensional quantum field theory with maximal supersymmetry. And if you put it on a 3-sphere times time, this is dual to type 2B superstring theory as a theory of quantum gravity on global ADS5 crosses 5 geometry, and more precisely into quantum gravity whose asymptotic boundary conditions are ADS5 crosses 5. And the type 2B superstring is a theory not just of low energy effective field theory, gravity, but it also has strings and D-branes and all the usual objects that string theory has. So what we're going to do is concentrate on this example and match some quantum field theory calculations to geometrical calculations. Okay. For the rest of the talk, I'm going to remind you, what are giant gravitons? What are giant magnons? Where does the nomenclature come from? And now the real plan is to put them together, to have giant magnons attached to giant gravitons. Basically, we're going to be computing the lightest open strings suspended between two D-branes. In a lot of this story, there's some formal parts of it that have to do with a central charge. There's a central charge extension on the world sheet of the string theory. And then this has an interpretation both in field theory and an interpretation on the gravity side, or on the string theory side. And then I'm going to tell you where this is going in the future and why it might be interesting to start looking at this again. Okay, so let me give you an idea of what a poor man's graviton is. Graviton is a massless particle. So you can think of a graviton as a classical point particle that travels on a null geodesic. The simplest one sits at the origin of ADS, and then it needs to move on a geodesic of the S5, and those are great circles. So once you pick which great circle you're moving in, this determines the null geodesic. It turns out that if you take any other null geodesic, they're conjugate to this one. This is a property of ADS5 crosses 5. So the idea is that we look at these geodesics, and the only quantum number that determines the family of these geodesics is the angular momentum of the point particle on the sphere, the angular momentum on the circle. It turns out that this object also preserves half the supersymmetry. Okay, there's ways to understand this. The nicest one that I like is that this is the thing that guarantees that the multiplet has spin less than or equal to 2. So that means that you can do low energy effective theory of gravity with it. So this is a poor man's graviton, but it turns out that there are stable D-branes, and a D-brane is a non-perturbative state in string theory. It's a soliton that has the same quantum numbers. What that means is that it has the same angular momentum on the 5 sphere, has the same amount of unbroken supersymmetry, and they can be point-like in ADS, but instead of being point-like on the sphere, they wrap a 3 sphere inside the 5 sphere. These are called giant gravitons. They were discovered by McGreevy, Susskind, and Tumbas in the year 2000. And let me tell you what the nomenclature is. We call them giants because it is an extended object and it has the same quantum numbers as a point particle. So if you were just looking at the main quantum numbers of representation theory, you would say that this is a graviton, but it turns out that these are extended objects. So we call them giant gravitons because you cannot distinguish them from ordinary gravitons by just looking at the representation theory of the conformal group. You have to do something else. Okay, so these are the first characters. So they're D-branes. And then if you have D-branes, D-branes are defined as places where strings can end. Okay. So part of the goal of this talk is to tell you how strings end on these giant gravitons and how to calculate their energies. Turns out that there's another giant graviton. It's also BPS. And instead of wrapping a 3 sphere inside the S5, it wraps a 3 sphere in ADS. And it also has angular momentum on the 5 sphere. So this giant graviton extends in ADS, but it's point-like on the sphere. And these were discovered by 2 groups, one by Hashimoto, Hirano, and Itzaki, and another one by Grisaro, Myers, Starford. They came out with their paper on the same day. Grisaro, Myers, and Tarford called it Goliath. Hashimoto, Hirano, Itzaki called it dual giant gravitons. So that's the nomenclature that basically took off. I don't like either nomenclature. I prefer to call them sphere giants and ADS giants, but this is still kind of the way it's treated in the literature. Okay, so the idea is that it's also BPS, it has the same supersymmetries, and you cannot distinguish it from the other giant graviton either. At least not from the point of view of representation theory of the conformal group. And then there's a field theory dual of all of these objects. So there was a complete classification of states that preserve half the supersymmetry. And it turns out that they all survive to strong coupling. They are protected by supersymmetry. And this classification was done by Corley, Javicki, and Rangulam in 2001. And they said all gauge invariant states of n equal 4 Yang-Mills as operators are classified by Young tableau. So if you give a Young tableau of SUN or of UN, you can write a state of the field theory that is half BPS. And then in these states, the energy is the number of boxes of the Young tableau. And what people call giant gravitons are column Young tableau, and what they call dual giants are rows. And ordinary gravitons are traces, and traces are sums of Young tableau of hook type objects. But the idea is that they all fit in field theory. So if you want to start in field theory to understand what these objects are, you need to start with these Young tableau, and you need to add stuff to them to decorate them with strings. So this is where we begin. There's other objects, which is how do you go beyond half BPS states? You need to consider more general states that have the letter Z. It's one of the fields of n equal 4 Yang-Mills. and that are decorated with some of the other fields of n equal 4 Yang-Mills. So you need to break some of the supersymmetry. And then the more general type of object is a type of traces with Zs and Ys. And if you start with a large number of Zs and a small number of defects, you can do Feynman diagrams to compute their energies. So what you actually produce this way, and this is something that was started as but really taken to in a paper by Juan and myself and Horacio Anastasi, but really kind of extended to a full integrable sigma model and a full integrable spin chain, was work by Minahan and Zarembo, Beiser and Staudacher, and Bena, Polchinski, and Royban. And the idea is that the ground state is a ferromagnet. So you turn the Zs into spin downs and the Ys into spin ups. And then if you just do this with Zs and Ys, you get an SU2 spin chain. SU2 spin chain is a ferromagnet. So it turns out that the spin chain that we get is in a ferromagnetic ground state. So it's not an antiferromagnet. That's usually where people who study integrable spin chains like to work because it's more messy, whereas the ferromagnet is more simple and by that token trivial. The excitations are spin waves, and the quanta of spin waves are called magnons. The magnon derives its name from magnetic, and the on is for particles, so these are magnetic excitation particles. Okay, so in Yang-Mills, there was a dispersion relation that was computed to all orders on the world sheet, or to all orders in the tooth coupling. And it was first conjectured by Santambrogio and Zanon in 2002. They said that this was a square root. There's Yang-Mills squared times n, that's the usual tooth coupling. And then there's some trigonometric function of the momentum on the spin chain. And the sine squared relation is typical for spin chain lattices. So the square root is the novelty that came out from the n equal 4 Yang-Mills calculation. And this was proved to be exact to all orders due to arguments of Niklas Beiser in 2005. And basically what he found is that the spin chain that you get in n equal 4 Yang-Mills has an extended symmetry. The infinite spin chain has an extended symmetry. And that extended symmetry, the supersymmetry, has a central charge. So when you consider excitations that carry that central charge, you find that there are BPS excitations. And when you have BPS excitations, the multiplet is short, meaning you have fewer degrees of freedom than a generic excitation. And that shortness is protected by supersymmetry. So the dispersion relation is basically controlled by that central charge. And the central charge basically involves this sine squared function of p halves. This is where the giant magnons are going to show up. So what happens at large P? If you start looking at large P, you get something whose delta minus J is of order of the square root of the tooth coupling. And that usually is associated with classical strings on ADS5 cross S5. So when we did a field theory calculation with Diego Correa and Samuel Vasquez in 2005, we argued that this angle interpretation was some kind of saddle point that we could compute in field theory. It was an uncontrolled saddle, so it was not a proof. But when we actually computed the saddle, this kind of distance from I to J, you could find that if you had a circle and the circle was some eigenvalues of a matrix model, and you had a radius, the radius will, or the thing that would control that dispersion relation was 2r times sine of the angle. And this was what was giving rise to that square root relation. And when we found this, we thought this was a disaster for ADS-CFT because this is a chordal distance, which is obviously not a geodesic distance between the two endpoints, I and J. And it's smaller than that distance. So we thought that there was a deficit in energy from what you could do on the CFT relative to what you were getting in ADS. And this is where the resolution of Hoffman and Maldacena came out. They were the ones who labeled the corresponding sigma model solutions on string theory, the giant magnons. Basically, what happens is that these strings, or a string suspended between those two endpoints that keeps on running in the Z variable, magnons, are relativistic strings. And because they are relativistic strings and they're moving, there are relativistic string motion effects that actually modify the dispersion relation. And it actually gives the correct dispersion relation. The giant magnon is a solution on the world sheet. It has that square root formula. It's a classical solution on the sigma model. And then the classical relativistic string soliton matches the field theory, the angles, and all. Okay. So when people studied these in 2006, they generalized it. They added angular momentum. So the original giant magnon didn't have an extra angular momentum, but people added angular momentum. And they found that delta minus J, which is the thing that controls the energies of these objects, is more generalized to a square root. And the square root has a unit of angular momentum squared, is an angular momentum on the 3-sphere if you started with these regular giant magnons. And then there's this same EML squared times sine squared of p halves. And then the central charge of Bicert is the difference in position on the plane. This kind of sine squared of p halves is an exponential to the IP halves minus exponential to the minus IP halves over 2. And this is what the central charge is controlling, is the square root, is the half that has the 't Hooft coupling. And then there's also an angular momentum squared. Now, what did they use to compute this? They found that this square root formula came from beta ansatz bound states. So there's a story about integrability on the spin chain. And then they also did sigma model computations on the S3 cross R to find this square root formula. So now we're going to put them together. And this is something that originally we started doing in 2004. So there was a paper that I wrote with Balasubramanian and Bo Feng and Mingxin Huang on how to attach strings to giant gravitons using Young tableau methods. So the idea is that when you do that, what you're doing is basically suspending strings between two tent poles. So this is how we hang our clothes into this line. We need the tent poles to suspend the string, and then we need to compute the energy of that string. Okay, so this took many years. There was basically, apart from us doing various computations, this Young tableau formalism was developed by the group of Robert de LAWGH in South Africa with a lot of his collaborators, and Sanjay Rangulam in the UK, and Hai Lin in China, and then Kimura, I think, was in South Africa for a while, but he's in Japan. And then there's also Yolanda Lozano. And I stopped counting because, you know, there's 13 years worth of works on the trenches on doing combinatorial calculations to try to get how this works out. So the main difficulty is that in the gravity side, the D-branes are localized. That they have some collective coordinate that puts them on one particular location. But if you start in a Young tableau, they have fixed angular momentum or fixed energy in the quantum field theory. And that if they have fixed angular momentum by the uncertainty principle, you are delocalized in dual angle variable. And it turns out that the energy of a string depends on the relative position between the branes. So it took a while to figure out how to get that collective coordinate in the field theory side. But we did it. But there's a little bit of a caveat too. These D-branes carry some angular momentum. The strings carry the same type of angular momentum. And the d-branes and the strings exchange an angular momentum. So spin downsides can hop on and off of the spin chain. So if you think about the spin chain as having a fixed number of up and down sides, this is changing the number of sides. So there's been a long story on the integrable spin chain side that once you go beyond the one loop calculation, the spin chain becomes dynamical, meaning the effective number of sides can change. And here you see that at one loop order, when you include open strings rather than closed strings, you actually get effects that also give you this dynamical spin chain problem, in that the number of spin sides on the string seems to be changing. So can we solve such a system? It looks like there's a variable number of sides, but what we discovered with Sam Vasquez was that you could bosonize the system, meaning you count the downsides between upsides. So if you go to a number basis of states where you fix the number of downsides, but you count how many or number of upsides, and you count the number of downsides between them, you get a bosonic spin chain, because there's an occupation number between the downsides. So instead of going to a y, z, 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 y basis, you count the number of z's between the y's. So you go to n1, n2, n3, and k. And then you can rewrite the spin chain, the integrable spin chain, at least the one for the SU2 sector, the x and y's, one loop order, in terms of some generalized bosons. So you write it as something that includes a hopping term, which is this kind of difference of raising operators and lowering operators between the different sides. And when you do that and you compute with the boundary conditions that we had on that we deduced from these spin chain calculations, we found that there was this extra term, which is a boundary condition, which involves some number lambda and lambda star. These are the collective coordinates that we found for the giant gravitons. And then we found that there was this extra term in the boundary that depended on these collective coordinates. So you have one such lambda for each endpoint. And what that means is that the spin chain feels the collective coordinate at the endpoints, which is the way it should be. Strings should know about where they end, only where they end, and the rest is solving the equations of motion. And then when we computed the energy, we found that the energy involved this GML squared times this difference of lambdas to the square power. And just to bring it back, these lambdas are Border square root of n. So in the original collective coordinate calculation, the lambdas were quantized to be of order square root of n. And then when you find GML squared times this difference of collective coordinates squared. And then the n is the number of y's in the problem, is the number of sides in the spin chain. And we did a 1 and 2 loop computation, so we reproduced this kind of square root formula to the first order in GML squared and to the next order in GML squared. And this looked like a square root, so we conjectured it was a square root. And this looks like a relativistic dispersion relation. N is a momentum, and lambda minus lambda tilde looks like a mass. And this is what you would expect if you have two d-branes and you separate them. The mass should more or less be proportional to a separation squared between them. Okay, so lambda is square root times a normalized coordinate, and this coordinate lives on a disk of radius 1, and I'm going to call them xi. So if you compare to these bound states of the magnons, the central charge is a difference of coordinates on a plane. So you find that the central charge should be this difference of coordinates times the 't Hooft coupling. So where does the plane geometry come from? So we found the plane geometry here. The plane geometry actually follows from the work of Hoffman-Maldacena originally on the sigma model of the string. Basically, you have to do the Nambu-Goto on time times a 2-sphere. That's all you need to find these solutions. And then what happens is that the giant gravitons move at spin 1 in this angle theta. So what we need to do is we need to do a rigid string solution, which is co-rotating and moving at the same angular velocity than the giant gravitons. And what that means is that the theta angle moves at the same speed as the time, and then the psi coordinate doesn't move in time. And then you can just compute the induced metric on this Nambu-Goto string. And if you do a direct substitution, you get this effective action. And then what you want to do is extremize for psi prime. Let me do a change of variables. You write a new radial coordinate, which I call cosine psi. And then you find that the action has a 2th coupling over 2 pi square root. And then there's a square root of the r squared plus r squared d theta squared. Most of you will recognize the square root as a line element on a plane in radial coordinates. So the minimal action is related to a geodesic problem on auxiliary flat plane geometry. So you basically draw a straight line between giants and you get the correct dispersion relation, meaning the distance between the two. And then I'm going to put in quotation marks that it's easy to add angular momentum. Easy means you solve the sigma model with an appropriate ansatz, and then you get the correct square root formula. And then what used to be the sine squared of p halves gets replaced by GML squared times n times the difference of these two coordinates on the plane squared. And then you do get to see the plane again, even when you add angular momentum. The ansatz looks not too different. The induced metric is much more messy. That's why I don't show it, but it works out. So this is what we get. Yes.
Sorry, warning system doesn't work. You have 3 minutes left.
Okay, very good. It's enough time. Okay, so now we're going to do the same with dual giants. This is what we just did. So now we do Nambu-Goto and ADS2 cross R. You do the same sigma model, except that now you do it, or you do Nambu-Goto, but now you see the ADS2 here because there's some time, there's some warping on the dt squared with a cosine hyperbolic plus the rho squared plus the theta squared. So again, we do a rigid string ansatz, t equals tau, theta is sigma plus tau. That means that theta dot is 1, which is the same motion that you get for the dual giant gravitons, and you make that rho dot is equal to 0. You compute the induced metric, and now the action again looks like square root of lambda over 2 pi integral d tau d sigma square root of hyperbolic sine squared of rho times rho prime squared plus cosine hyperbolic rho squared. And now to find the plane, you do change of coordinates where you make r equals to cosine hyperbolic of rho. Okay. And what that means is that dr has a sine hyperbolic of rho times rho prime. And then you find that this part is the r squared and this is r squared d theta squared. Now there's going to be some observations. We get an analytic continuation of the solution of the sigma model in the sphere times time. In the other one, we had that the radial coordinate was cosine theta. I cheated by doing the sphere coordinates in the right coordinate, which was slightly different than the usual coordinates on the sphere. What we find now is because r is cosine hyperbolic of rho, is that the radial coordinate r must be outside of a disk of radius 1. And then rather than having a disk of radius less than 1, we are outside of a disk of radius 1. We can add angular momentum easily, but it is on ADS rather than the sphere. And we get the same result of a square root of energy square root of g squared plus g Young-Mills squared times n times the difference of these coordinates on the plane. The difference is that now the string can touch the circle even if the two dual giant gravitons are outside the disk, because the chordal distance between them can accidentally touch the inside. So if r gets to be less than 1, the rho, because r is equal to cosine hyperbolic rho, acquires an imaginary part. So what happens is that these strings are not allowed to penetrate inside the disk. The state does not exist. And then delta and J diverge close to when you try to get them past the disk. So there's something unphysical. The dual giants are also related to a Coulomb branch of n equal 4 Yang-Mills. This was originally discovered when the dual giants were discovered. So you're kind of going to a Coulomb branch of n equal 4 Yang-Mills. The open strings between the D branes for the Coulomb branch of n equal 4 Yang-Mills have to be BPS. This is in some sense that when you separate D branes, you need a short n equal 4 Yang-Mills multiplet between them. So the spin is less than 1 or less than or equal to 1. So they should be BPS. The central charge of BICERT needs to be the same central charge of the Coulomb branch of n equal 4 Yang-Mills. This is an argument I was making in 2014, but now we're doing a straight string computation. And then the plane geometry that shows up, this disk that shows up is actually the LLM plane. This was originally pointed by Hoffman and Maldacena. And now we can extend this to all have BPS solutions of supergravity, which is work in progress. Okay, instead of giving you conclusions, I'll give you an outlook. You can think of this as another set of checks of ADS CFT. Why? Because we have some way of understand how to do the computation on the CFT side, at least to some loop order. And on ADS, we can do the sigma model, we can do the loop computations. But now we can do it with branes that are involved in the radial direction of ADS. Locality in the radial direction of ADS has always been more messy to understand, and this gives us a handle on it. One other thing that you need to understand is that the giant gravitons source the central charge for open strings, so that the strings carry a central charge which depends on the position of the giant gravitons. It's the same thing that happens for strings in flat space. When you separate D branes, they source the central charge of the string sigma model. And the central charge on the string sigma model ends up being the central charge of the Coulomb branch of n equal 4 Yang-Mills. The LLM plane geometry emerges naturally from these rigid ansatz. It's some induced effective metric that shows up. We're currently extending similar computations to all LLM solutions. There's a nice story of this being an analytic continuation between the sphere and ADS. This has always been the case that the sigma model on ADS5 is an analytic continuation of the sigma model on ADS5. But one of them is compact, the other one is non-compact. One has an SU2 sector. The equivalent thing in ADS5 is an SL2 sector. This has infinite dimensional representations, and it's always been less well understood. And then the dual giant physics requires this SL2 story to be better understood. The SU2 story had a relation between the beta ansatz, and now we need to figure out how to extend this beta ansatz story to the SL2 sector to make a connection more precisely with the solutions that we have on the string sigma model. And if you go beyond dual giants that preserve the same half of the supersymmetries, but that preserve a quarter of the supersymmetries, there seem to be corrections. There are going to be power series in the tooth coupling. And because there are corrections on the string sigma model side, we should be able eventually to reproduce them using the quantum field theory technique. And that should be very interesting because that's a new source of calculations where we have something new to compute, where we have an explicit tooth coupling calculation on the string theory side that we can try to understand using field theory methods. And the computations are going to start getting corrected at 2-loop order. It's not going to be a 1-loop order thing. So we need to work hard, and we need to work hard in the SL2 sector to figure it out. And that's all I have to say. Am I on time?
Thank you. Yes, yes. In fact, we have 5 minutes for questions still.
Thank you.
Are there questions? Carlos, please. Carlos Núñez.
Yeah, here I am.
Yes.
David, so there was something that I did not capture, that is what you, when you explain about this string that was going in a chordal direction and not having the possibility because of the change of coordinates to enter inside the radius equal to 1. Yeah.
Yes.
Are you with me? Yep. And then you said there are you missing solutions? And then you make a connection with LLM that I completely miss. How from there you induce the LLM geometries.
Okay. So let me go back. This is the induced metric on the worldsheet. Can you see it? The D squared induced?
Yeah.
Okay, so what you see is that the TT component or the tau component has this -1 plus cosine squared of psi.
Cool.
Okay, there's an angular velocity of the psi of the theta in here. So the fact that theta is moving at angular velocity 1 is the one that gives you -1 plus cosine squared of psi.
Good.
It so happens that the -1 plus cosine squared is this sine squared of psi. Right? This is trigonometric identity. Then when you compute the determinant of this, which is what goes in the sigma model, you get a sine squared of psi times psi prime. And then for the cosine squared, this cosine squared cancels out and you only get the term that comes with the -1.
Okay.
So this is how you get this sine squared psi, psi prime squared plus cosine squared of psi. Okay. Now, when I go to the radial coordinate is cosine of psi. And then you get this plane geometry coming out of nowhere.
Good.
Now it turns out that you can track this radial coordinate or this angular coordinate to the collective coordinate of the giant gravitons itself. So we know where these giant gravitons are. We can actually compute where they are. And these giant gravitons are usually represented as points on the LLM plane. It turns out that these coordinates match the LLM plane.
Okay.
So the connection to the LLM plane is kind of that one. And the same happens for the dual giants. So for the dual giants, these collective coordinates are the ones that you would get from the Coulomb branch from n = 4 Yang-Mills.
Okay. Okay. Right.
And this is where we know that we actually landed on the LLM plane and how it came about. I know I went fast.
No, it's okay. It's okay. I understood that you created the LLM geometries. Sorry, it's okay.
I have to thank Juan for finding them. Otherwise, I would.
Yeah, of course. So you had a comment where you mentioned the central charge of the open string is the central charge in the Coulomb branch.
Yes.
Is the field theory in the Coulomb branch of n = 4 in this case.
Yes. So that's again because in n = 4 on the Higgs branch, there's a central charge that controls the W bosons of n = 4 Yang-Mills. And then when you take dual giants, you're exploring the Coulomb branch of n = 4 Yang-Mills on a sphere rather than on the flat geometry. Okay. But the point is that if you do a semi-classical computation to leading order, you get the same square root formula. And the reason why you expect a central charge in n = 4 Yang-Mills is that that's the only way to get a short multiplet that has spins less than or equal to 1. It's a well-known fact about that Coulomb branch.
Okay. Good.
And the point is that the shortness condition on the string sigma mono side also comes from a BPS condition, otherwise you would have too many states. And then what happens is there's two central charges and they both are there for the same reason, which is to reduce the number of degrees of freedom. And asymptotically for large C, you go really in the flat space limit, and there you can see that you're matching the same central charge.
Thank you. We have exactly time for the question of Diego Correa, please.
Hi, David. Hi, very nice talk. So I think my question is related to Carlos' question, the first one. So you said that, I mean, by doing this change of coordinates to this LLM plane coordinate, you show that the rigid straight line solves the Nambu-Goto equations of motion, right?
Right.
So the question, I mean, you show it for the string in the case of the circular droplet, but I guess that you can do the same for any arbitrary LLM geometry. That is the question. I mean, this change of
this is exactly what we're doing with my student. With Adolfo again, we're doing exactly that. The warp factors are just so that they cancel out. The TT and the sphere kind of things have some functions that are inverses of each other, and that kind of seems to do most of the trick. We're doing some things with gauge invariance, checking that this is invariant under various changes of coordinates in the LLM geometries, because there's some gauge potentials in there that can float around, and we're trying to see if we can extend it to other half BPS geometries that would have, let's say, ADS3 crosses 3, and there we doesn't seem to work. They also have bubbling solutions of similar kind, but it doesn't seem to work. But we're trying to figure out how much we can push it further. We think LLM is solid. These divergences and these analytic continuations, we're trying to understand better what happens when you change colors on the LLM plane, because all of these things go bad when you try to suspend these strings, these rigid lines, and make them go between regions that change from one color to another. And this is the same thing that we saw here, that you can't send that straight line through the sphere, but we need to understand a little bit better what's going on. And part of it is I think that we're supporting angular momentum on this string, and you are actually on the LLM plane. And once you go inside the other color, that the sphere on which you're supporting angular momentum has shrunk to 0 size. And part of the solutions of the Nambu-Goto string are that the density of angular momentum is constant, and you cannot support angular momentum at 0 size. Right? You're at a singularity of that angular momentum. But we're trying to understand better what's going on, how they really become unphysical. Okay, this is where we're at. This is the stuff that I hope we'll be able to push through in the next 2 weeks. Hopefully. Coronavirus has a way of interfering with my job.
Okay, thank you very much.
Thank you very much, David.
You can continue discussion in the discussion session, and if there are more questions, you can ask in discussion session. We will meet in exactly 5 minutes at 11:37.
Okay.
Thank you.
Thank you.
Hello.
Hello.
Hey, can you see
Thank
my
you.
slides?
Yes. Yes, they're perfect.
Can you see the mouse as well?
Yes, it is
Oh, perfect.
visible. Yes. 5 minutes before the end of your talk, I will put music like ring, but probably you won't hear it well. So I'm sorry, I will interrupt you.
No problem. Cool.
Yes. Maybe we can already start. Okay, so I have a pleasure to introduce the next speaker, Ignacio Reyes. He will tell us about, from Albert Einstein Institute, and he will tell us about quantum extremal islands made easy.
Okay, thank you very much, Olivera, for the introduction, and thank you for the invitation. It's a great pleasure to talk here. I would also like to congratulate the organizers of this initiative, which I think is really great. Okay, so yeah, today I wanted to talk about quantum extremal islands and how can we make them a bit easier to understand. And this is based on work with this awesome group of collaborators, Vincent Chen, who is a student at PI, Rob Myers, Dom Neuenfeld, who is a postdoc at PI, and Josh Sander, another student at Brenner. Okay, so here's the outline. I'm going to start with a very short reminder of the information paradox problem and how this has fueled a lot of the recent discussion in, say, the last 12 months or so. Then I'm going to introduce our model, which is a story of islands on the brain. And finally, we're going to talk about how can we extract the page curve from a very simple model of a black hole. Okay, so as we all know, the information paradox is a very old question, which was pointed out already by Hawking himself. And the question was to keep track of the Hawking radiation as time evolves and the black hole evaporates. So one way to see that is, say, consider the Penrose diagram here of an evaporating black hole. So there's some matter that collapses here, it forms the horizon, and then this thing evaporates. So in this diagram, this green line over here represents some cutoff slice far away from the horizon, whereas these blue lines represent space-like regions where we collect the outgoing Hawking radiation that escapes towards infinity, and these different lines correspond to different times. So we want to study the time evolution of this problem. In this particular picture, I've only depicted one single pair of Hawking modes, one living inside the horizon, and the other one is escaping towards infinity. Okay, so then how does the evolution of the entropy look like? Well, at early times, so let's assume that we start from a pure state, that the collapsing matter started in a pure state. Then the entropy of the Hawking radiation starts at 0. But then, of course, as pairs start to create, you see they are collected by these future slices. And whereas the outgoing Hawking partner is collected, there's the purifying partner, the partner inside the horizon, is not collected by those slices, and that contributes, say, log2 or 1 bit of to the entropy of the radiation at infinity. So this process just continues to go on, and that causes the entropy of the radiation to rise. And in principle, nothing stops this until the point where the black hole completely evaporates. So the evolution, sorry. So this, in the lower panel, we have a plot of a sketch of this process. So the red line is supposed to represent the radiation that has escaped, and this thing simply continues to grow. And of course, it was pointed out, well, by Hawking himself, but then it was quickly understood that this is in contrast with unitarity, because the initial state of the system was pure, the final state of the system is going to be mixed, and then we have a problem with quantum mechanics. So Page pointed out early on that the correct result that we should get from a correct account of the entropy should look something different. So you can consider now measuring the entropy of the black hole itself, say measured by the area of the horizon. And that is a curve that is going to start at some finite value, say a large value when the black hole forms, and then it's going to drop as the evaporation goes on. So Page said that the correct curve we should expect to get should first rise as the Hawking calculation suggests, and then go down with the black hole entropy. Now, the big question was, how is this supposed to happen, or what is the physical principle that explains how to get this curve? So in 2019, we found some new answers to this problem, and we saw a sort of breakthrough in our understanding of how to reproduce a Page curve simply from semi-classical gravity. And here on the right, I have some of the important papers, initial papers on the subject. And to summarize it in one line, this is related to what we've already heard before today, what's known now as the island formula. And essentially what it's saying is that when we do the calculation that we were just talking about, computing the entropy of the radiation, we're actually allowed to do something extra that we didn't know we were allowed to do before. Namely, the entropy, the spatial region that we're, to the spatial region that we are, where we're collecting the Hawking radiation R, we can add some arbitrary space like disjoint region I, which is called the island, which might live in the black hole interior. So now we're supposed to compute the semi-classical, in the semi-classical approximation, the entropy of the region R union the island. And there's a price to pay if you introduce an island, and that's that you have to add the area term corresponding to the boundary of the island, which in this picture corresponds to this term over here, divided by 4g Newton. So I just want to point out that this is not a formula that you sort of, you know, shooting by hand, but it's not, rather something that you can derive from first principles. And we'll hopefully come back to this later. Now, the last point here is that this formula, as we also heard today, seems to be mostly useful when we have matter or degrees of freedom that are entangled between a region that has dynamical gravity, in this case, the black hole region, and some other region where gravity is non-dynamical. There's no gravity. In this case, where the radiation goes towards infinity. Okay, so this formula, we've heard a lot about it, and there's very good arguments supporting it, but it still sounds a bit mysterious. So the task we set up ourselves was, well, can we find some setup where we can make this very easy to understand? So here are some of the concrete questions we're trying to address. Can we put this island formula in a more familiar holographic setting that we're sort of more used to? Then what is a natural setting where we have this situation where we have entanglement between a region with gravity and a region without gravity? Also, most of the explicit models that have been worked out are in 2D. But of course, since in 2D gravity is sort of trivial, people have looked at JT gravity, which is slightly more exotic. So we were trying to understand, well, how can we bring these ideas into higher dimensions, and can we do it simply using Einstein gravity instead of some other theory of gravity? And finally, well, how relevant are islands in general if we're not talking about black holes? And certainly today we saw an example with the first talk where this was precisely the case. Okay, so let's jump to the concrete thing we were looking at, which is working with islands on the brain. So here's the model that we considered. I'm picturing here a constant time slice of the geometry. We have an ADS, a pure ADS bulk in d+1 dimensions, which comes with 2 scales. That's the L, a capital L, which is the ADS radius, and a bulk gravitational constant. On top of that, we're going to have a brain, which is running sort of through the middle of the space-time. And we want that the induced metric on that brain is also anti-de Sitter, but of course, since it's going to be a codimension 1 brain, it's going to be ADS in 1 dimension lower. Now, this brain is going to come equipped with its own gravitational coupling, G-brain, which is going to be independent of G-bulk. So that's the story in the bulk. When we look now at the boundary, we have, of course, as usual, a holographic CFT, where gravity is freezed. So the asymptotic boundary is going to play the role of the region where there's no gravity. In the previous example, that's the Hawking radiation going towards infinity. Now, the location at which the brain intersects the asymptotic boundary, at that location, there's going to be a conformal defect. So this is actually it's going to be a CFT coupled to a conformal defect living at the equator of the sphere. So this is sort of the higher dimensional picture of the model proposed in this paper. And there's also a close connection with a group of these other people. Now, I should also mention that this idea of looking at the physics of ADS brains embedded in some higher dimensional anti-de Sitter was worked out, as far as I know, initially by Cash and Randall in this beautiful paper, where, okay, they were the first ones to look at really to go through the Randall-Sundrum procedure. Okay, so here's the first sort of take-home message that I want to put forward. This is the formula we want to advertise in higher dimensions. So let's look first at the picture. So what is the quantity we want to compute is going to be the entanglement entropy of some regions on the boundary. In this particular picture, it is the union of 2 disjoint regions, 1 on each side of the defect. And the statement is that the correct formula that gives the entanglement entropy on the boundary of this region is given by a sum of 2 terms. The first term here on the left is the standard RT Ryuta-Kainagi formula. So V is going to be here a codimension 2 surface that is anchored on the boundary of R, on the asymptotic boundary. And this contributes simply the area of that surface divided by 4G bulk. That's the standard RT formula. Now, the new statement is that if the Ryuta-Kainagi surface intersects the brain, so if this V intersection brain is not empty, then we have to add an extra term, which is also an area term, but it's the area of that intersection divided by 4G brain. So notice here that the intersection of V with the brain, which I'm trying to depict here by these small red dots, it's the area of that thing that enters the formula. Now, of course, importantly, if the RT surface is intersecting the brain, then the region whose boundary is that intersection is precisely an island from the point of view of the theory on the brain. So the second term over here is precisely the island contribution to the previous formula. Okay, now, of course, if the RT surface does not intersect the brain, this term simply cancels and we get the usual RT formula. Now let's try to understand a bit where this formula comes from. So what is the bulk picture? So the total action of the system is going to be the sum of a bulk action and a brain action. The bulk is simply a standard Einstein-Hilbert term, which comes with the two couplings, so G bulk and the bulk cosmological constant. And for the brain, we're going to have the standard Randall-Sundrum term, which comes with the tension of the brain, which is effectively a cosmological constant. Here, G tilde is the induced metric on the brain. And on top of that, we're going to add the Ricci scalar on the brain divided by the brain gravitational coupling. So the question that now we have to answer is, well, what is the theory, what is the effective theory of gravity that is being induced on the brain? How do we do that? Well, we do essentially the same thing that we do in standard holographic randomization. We integrate the on-shell bulk action up to the location of the brain. Of course, in usual ADS-CFT, what we do is we integrate it all the way to the asymptotic boundary. This yields a series of terms that depend on the geometry, on the curvatures and so on, which is the expansion that we have over here. But in that case, this expansion comes with a series of divergences, which we subtract by adding counter terms. Of course, in this case, when we integrate towards the brain, since these terms are not divergent, we're going to keep them. And that is precisely what yields, that makes gravity dynamical on the brain. Okay, so once you do that calculation, and this is, as I said, a very familiar calculation in holography, the result that we get is here, is this effective action. So there's two important couplings in this action. First of all, there's the effective G Newton. Oops, sorry. There's the effective G Newton on the brain, which, as you can see here, is not only given by G brain, but rather a combination of G bulk and G brain. That's one coupling. The other important coupling is the effective ADS radius on the brain. Now, this, of course, is going to be proportional to the Ricci scalar of the induced metric on the brain. So then, and the Lagrangian that you get is, of course, an expansion. And the important thing here is the following. The first two terms are of the same order and our standard Einstein-Hilbert term. And then all of the higher curvature corrections come with some coefficients, and those coefficients are controlled by the ratio between the bulk ADS radius and the effective brain ADS radius. So one way to make this story easy is to restrict to the regime where this ratio is very small, such that all the contributions from these higher curvature terms vanish. And we have effectively, or to a very good approximation, we have Einstein gravity on the brain. So now that we know what the action is, well, we can go and try to understand where this formula comes from. And that is, as usual, simply the gravitational path integral. So in the literature, we've seen how to understand, that the island formula arises from the so-called replica wormholes, which are simply non-trivial topologies in the path integral that is computing the Renyi entropies of the system. And of course, that formula is correct. That approach is correct, but it's slightly non-intuitive. So in the brain model that we're using here, this formula comes in a very intuitive way. That is simply the fact that, as usual, we do the same calculation. As always, the gravitational path integral is approximated by the saddle point. And it's simply the fact that the total action contains a bulk and a brain term, which, when you compute the entropy, gives us the two terms that we were talking about before. So here I would also like to point out that, as you see in this picture, there's some interesting physics related to these islands that is present there even in the absence of black holes. Although the formula was presented maybe at the beginning in relation to the information loss problem for black holes. And we studied that in this paper, but well, I won't go into much detail on that now. So what I wanted to talk about now was, well, now that we know what the setting is, how can we understand or reproduce a page curve in a very simple model of a black hole? Okay, so here's the same picture I was showing you before. On the lower left, we have the bulk ADS and the brain cutting through the middle. Above this, I have essentially the same picture, but I've added global time. So here the cylinder is the usual, ADS in global coordinates. And you see there's the brain that is cutting through the middle. And we can't see what's hidden on the other side of the picture. So the bottom picture is simply the top view of the above picture. So now what we want to do is to make a black hole appear in this setting. How do we do that? Well, there's a very simple way, which is called this topological or hyperbolic or Rindler ADS black hole. And that goes as follows. Just as in flat space, when we change coordinates to Rindler coordinates, we get some interesting metric which does not cover the entire space-time and also induces, it has a horizon. In the same way, you can change coordinates in anti-de Sitter and get what's known as the Rindler ADS metric. And just as in flat space, so what you get is two horizons here, which is sort of depicted by these blue or purple null surfaces. And the Rindler coordinates only cover the two exteriors of that. So it's sort of the regions to the right of here and to the left over here. So now if we again look at the top view, the bifurcation surface, which is the place where the horizons meet, is shown here as this dashed purple line. And just to ease the understanding of the geometry here, I've placed this orange dot, which is going to be the same in every picture. So here I place it at the point where the bifurcation surface reaches to the asymptotic boundary, which in the top view corresponds to this point over here. Now, we said that we would like to compute entanglement entropy of some regions on the boundary theory. And here I'm showing the same regions as before. So we're going to focus on two disjoint symmetric regions, one on each side of the brain. Now, what's happening on the boundary of this picture? So, well, you need a bit of imagination to see this, but when you take the Rindler coordinates and you take and you go to the asymptotic boundary, you will see that these two triangles or diamonds on this picture becomes these two diamonds. So you have one on the right and one on the left, and they're joined on the part of the picture that is behind that we cannot see on this point over here. And here again, I put the orange dots, which are supposed to, you close this picture to form the cylinder. So these are identified on the front of the picture. So this is the CFT point of view. The region is going to look something like this. And of course, there's the defect crossing in the middle. So it's important here that these regions are not touching the conformal defect. So now what we want to understand is, well, how to compute the entropy of these regions, and especially how to time evolve, how to compute the time evolution of the entropy. So what is time evolution in these particular coordinates? I told you we're looking at Rindler coordinates. So from the point of view of the boundary, if you evolve in Rindler time, the evolution looks like this. So as time passes by, we're computing the entropy of these regions over here. And as you can see from this picture, the endpoints of the region move closer and closer to the location of the defect. In the top view now on the left, the same thing is happening. We see that these black dots, which are the endpoints, they come closer and closer to the defect. So that's the evolution that we're looking at. Okay, so how do we do the calculation? Well, now things become very easy because we simply use the extended RT formula. And the whole point of this construction was to make things very easy. And now you can see the point, because in this calculation in the bulk, we have reduced the computation of the problem of the page curve to simply the problem of two intervals or two disjoint regions in ADS, which is something that we've been dealing for a long time. So the story is that at early times, as we said, time evolution is making this region larger and larger. So at very short times, this region is going to be small, and therefore the RT surface is going to be disconnected. And the entanglement wedge as well, the shaded region here is also going to be disconnected. Now, as we all know, since at least the ones who've been working on this field, we have to find the minimal that is homologous to this black region. And at some point, when time passes by, this black region becomes larger and larger, and there's a phase transition where it's now more convenient to connect these dots in this way compared to connecting them in this way. And the entanglement wedge is now connected. So this is simply a phase transition of two intervals, which is something that we've known for a very long time. Now, of course, in this phase, you have to add the contribution, the island contribution, that is the contribution of the intersection of the RT surface with the brane. And of course, when that happens, we get an island on the brane. So,
excuse me, you have 4 minutes.
Thank you very much. So this, as we see, is simply a phase transition in the RT surface, which has been known for a long time, and which was also initially linked with the Hawking page transition. So if you now plot this thing in time, the evolution of the entropy of the radiation, at early times, there's the rise, which corresponds to this phase. And at late times, when this other phase dominates, it's not obvious from the picture, but due to the sort of the magic of the coordinates that you're using and so on, it turns out that the generalized entropy is simply a constant. That's why we get a constant over here. And it doesn't go down as in the original page curve, but that is precisely what it should. This is the correct result, because we're actually looking at the eternal black hole. We're not looking at a black hole that evaporates. So this is the actual page curve that we should have got. And finally, the value at which the entropy saturates is given, for instance, in terms of the tension of the brane that we're using. Okay, so in summary, we saw how islands can become a little more intuitive if we use this Randall-Sundrum brane model. We showed how you can use this approach to understand the island formula and this sort of island physics in higher dimensions. And we used it to understand a very simple model of this topological black hole and how to reproduce a page curve in that context. Of course, there's many questions. One of them is, well, what about more realistic black holes? We looked at something which is like a Rindler black hole, but what about putting real black holes in the bulk? There's a very interesting issue, which was known originally by this paper from Carson and Randall, which was that actually the theory on the brane has a massive graviton propagating. And this was pointed out as well recently in this paper. So there's some interesting physics to understand there, and it's not very clear what the role of this master graviton is for the story of the islands. And finally, a question that I think we've all been puzzled with and asking in recent times is, well, okay, fine, we were able to understand how to reproduce a page curve, but how is actually the information, you know, if you throw the diary into the black hole and then it evaporates, how do you recover the information of the diary purely from the radiation? And that's an open question that is something very interesting. So that's all, and I thank you very much for your attention.
Okay, thank you very much. Are there questions? We have some time. Carlos, please. You can ask.
Ignacio,
Mm-hmm.
can you hear me?
Yeah.
So the question, thanks very much for the talk. I understood many things that I didn't before. The question is the following. Suppose that instead of a defect brane, right, you have a full solution that corresponds to defect conformal field theories. For example, an ADS4 inside ADS5, or Good-Perle have worked out many examples of them. Do you expect the same thing to happen in that case? So if you have, instead of the defect brane, as you have, basically the back reaction of this defect, so fully defect conformal field theory dual solutions, do you expect the same thing to happen? And what will, in that case, what will disconnect the Ryuta-Kayanagi to fall into the, say, smaller ADS2? I don't know if I'm clear in the question or if I should make it clear.
I didn't follow. I mean,
right. So what I'm saying is, what's happening to your Ryuta-Kayanagi surface is that at some point, yeah, okay, that exactly. At some point, it likes to sit on the defect brane, right?
Mm-hmm.
So suppose now I don't have the defect brane, I just have the solution with an ADS inside the other. Do you think this calculation will go similarly?
So which ADS inside which ADS?
So let me take for an example, one example of the many that exist, ADS2 inside ADS3, right? Okay. So there are solutions where people have constructed, and these are dual to 1D defects inside 2D CFTs, but there are in different dimensions, right? In that case, do you see these dynamics that you are pointing out here will also occur there?
And what is the action that you take there in the bulk?
So the idea would be that in the bulk you don't have the action of a brane, but you have a full supergravity solution, right? That has a region with ADS3 or ADS4 or ADS5 as you wish, and an internal zone. Look, if you want, we can discuss it in the discussion session.
No, it's a very good
I know
question.
you didn't do this calculation, so I'm asking if you had any intuition.
I don't see any reason, in principle, I don't see any reason why it should not happen.
Good.
But I would love to have this discussion.
Yeah, we'll talk it
out. Yeah.
Okay. No problem.
Okay, perfect. The next question is by Diego Correa. His application does not work well, but I saw him. Is it true, Diego?
Oh, sorry. I think it was, I accidentally probably clicked and right.
Okay. Okay. So, okay, thank you. So the next question is by Alberto Guijosa.
Yes, thank you. Hi, Ignacio. Thanks for the nice talk. So you, as you say, you're making intuitive the fact that you have this island and the transition to it using the bulk perspective, but you also mentioned that from the brane perspective, you have, well, this island formula you can deduce through the usual replica wormhole story. Now, my question is, if you resort to these replica wormholes, wouldn't you have the factorization problem that people have been discussing? And then if you have that problem, how does that not go against the fact that you manifestly have a single unique quantum theory rather than an ensemble?
It's something that we don't yet understand. It was also a question for us because, as you say, it seems that here we're not looking at an ensemble of theories, So originally we thought that this would be an example which would show that you actually don't need to have an ensemble of theories for the island formula to work. But I guess it's something, that's what we thought when we started this project. And I think that now we're trying to see how to connect this to these ideas. But our original motivation was precisely, or one of them was precisely to show an example where you don't need to have this issue and you still find the islands anyways.
Okay, thanks.
Okay, thank you very much. There are no more questions, so I would like to tell you that now we will have 5 minutes break and we will meet at 12:16. Before that, also, I would like to introduce the next chairman for the afternoon session, and that will be Leopoldo Pando Zayas. So I'm giving him the screen. Thank you.
Hello. Okay, so looks like we're back. Andres, are you able to share your screen?
Yes.
All right, so welcome to this afternoon session. Our first speaker is Andres Anabalon. He will tell us about symmetric traversal wormholes, please.
Thank you, Leo. Well, thank you, Elena, Tomas, Alberto, and Mariano for organizing this nice conference. I will talk about this work that I did together with Bernard de Witt and Julio Oliva. The outline of the talk is this. I will make a historical introduction about wormholes. I will talk about some very general results about topological censorship, and I will discuss how we evade these results. I will discuss some special coordinates that we use to this end. I will show how you can make by identifications in global ADS, you can create a spacetime which is non-simply connected. I will discuss what are the killing vectors and killing spinors of this spacetime after identifications. I will discuss how the boundary of this space that is ADS with identification is connected. And then I will generalize this to some non-constant curvature case. I will discuss the supersymmetry of this mu space. And I will show how the boundary of this mu space is disconnected. And then I will discuss what we expect to do. So the term wormhole comes from a paper, first appeared in the literature in a paper by Fuller and Wheeler. And they comment that another paper given by Weil have this idea of having spacetimes that are non-simply connected. This is the mathematical translation that of the common idea that within the same universe it's possible to travel between 2 points using two alternative paths. The standard picture one has in mind is well represented in this figure of this paper that I will reproduce now. And the fact that this is just a tunnel in the space-time means that you have a single boundary. This is I make this remark because many people think that to have a wormhole you need more than one boundary, but this is not true. If you could have a wormhole between our galaxy and the next galaxy, and Andromeda, this will be a wormhole in a space with a single boundary, because it's within the same universe. So this is the idea that this is the figure that comes from this paper of Fuller and Wheeler. And this essentially the thing is that a wormhole is a space that is non-simply connected. So you have a handle. So I would say that mathematically, a wormhole is a everywhere regular space-time that is non-simply connected. Okay, and you don't have closed-time lectures. You don't have any kind of pathology such that it's a good space-time. There is another kind of wormhole that is the Einstein-Rosen bridge. The Einstein-Rosen bridge is this bridge or wormhole that connects the two regions, the two asymptotic regions in an eternal black. This wormhole is non-traversable, is different than the wormhole that Fuller and Wheeler discussed. And because you have horizons, okay? So in this case, you have two regions that are like two boundaries that are disconnected, and you have a wormhole, but you cannot go, actually, you cannot send information to this wormhole. And this is very different than the idea of Weil, okay? So now some people, well, after some results of Witten and Zhao, where they consider what happened, whether one can have wormholes in Euclidean ADS. And they prove that in general this is not possible unless when the boundary has positive curvature, or in general when it's not negative. Later it was proven that when it's not negative, you cannot have wormholes. But then some people generalize these results to the Lorentzian case. In the Lorentzian case, there is this general, relatively general theorem that is by Galloway and other people that says the following. They said, let N be a globally hyperbolic spacetime with a boundary, with time-like boundary I. That satisfies the average null energy condition. Let I not be a connected component of I. And let us assume that I not admits a compact space like cat, or N satisfies the generic condition, then I not cannot communicate with any other component of I. So what they have in mind here is that, so for instance, a spacetime that satisfies all these conditions is a global charged ADS black hole. And you have two boundaries, so you have two connected components of I, but this you cannot send information between them. Okay. Here they mention something called the generic condition, and the generic condition is this thing that we have here below. Okay, that is a contraction between the tangent vector to some time like Arnold geodesic and the Riemann tensor. So you need that this is different from zero at least in one point along the geodesic, or that the boundary is compact. In the space section, the spatial section of the boundary are compact. So well, however, if you put ADS here, you can see that ADS has this equal to 0. Okay, so since ADS has this equal to 0, one can try to construct traversable wormholes by identification of ADS. And actually, this was already done in the Euclidean case by Maldacena and Maus, where they make like all the directions that are orthogonal to the radial direction in which you traverse the spacetime. They make all this compact spacetime that breaks all supersymmetries, and that they later also study whether these wormholes are stable, and they found that this is not stable. But I will study this case now. Okay, I will start studying ADS, and I will show that it's possible to construct a non-simply connected spacetime that is well behaved, and then that in which I am avoiding this topological censorship theorem, because this is 0 and because I am considering spatial sections that are not compact. So I want to discuss a little bit the coordinates that I will use. This is the coordinate that you are all familiar. This is what is called the global coordinates in ADS, where you have foliation by spheres of the spacetime, and where you of course consider the universal covering, and this is what is called ADS. I will use this other foliation where you have a foliation of ADS by ADS trees. So here you have ADS tree. There's actually a fibration that is written as a Hopf fibration, let's say, over ADS2. So here immediately you can see that this coordinate d to the u, you can see that the Killing vector d to the u has never vanishes. So this means that the axis of symmetry d to the u is not within the spacetime. There is somebody saying something in the chat. I cannot see the chat, but somebody is saying something. So if we make an identification here in d to the u, such that we make this coordinate compact, because this is global ADS when all the coordinates are not compact. We make d to the u compact. This spacetime is automatically non-simply connected, because all the loops that goes around d to the u are not contractible. Okay, so I will now pass to study this spacetime that is global ADS when d to the u is compact. Okay, and also you can see that this when r is equal to 0, the S1 or the norm of this d to du is minimum. So this will be the throat of the wormhole. Okay. When you make this identification, you lose 6 Killing vectors, because all the other Killing vectors are hyperbolic functions of u. So they are not single valued when u is compact. So you lose, and you lose 6 Killing vectors, and the symmetry of this space-time are these 4 Killing vectors. But actually the ones that live invariant part of the ADS3. Funny window appearing. Maybe I will stop sharing and I will do it again. I will do it. Now it's gone, I hope. This funny window. Yeah, I also see something funny. Okay.
It is gone.
Huh?
It is gone, but it's, I mean, one can still look at understand what you're saying and what is on the screen, but so it's not a big deal. Go ahead.
Okay. So now, so the Killing vectors went from 10, that is global ADS, to only 4 after this identification. If you compute the Killing spin-offs in ADS, you have, well, 4 for every supersymmetry. Okay. So these are 2 of these guys, and you can see these 2. You lose also these 2 Killing spin-offs because these are also non-single valued functions of u when u is compact. So you lose these 2 guys, but you still have these other 2 in these coordinates. Okay. So supersymmetry is broken to 1/2 after this identification is done. Now let's see what is the boundary of this spacetime. This spacetime have this boundary, obviously. So because when r is go to infinity, you get what you have within this, what is multiplied by r squared in the metric. And this is ADS3. And of course, ADS3 can be written in this way. That is half the sphere times this conformal factor. And this is why, like, one of the boundaries, because this, you can see, like, I will go back to this metric. You see, this metric r goes within plus infinity and minus infinity. So the boundary when r goes to plus infinity is the same boundary that when r goes to minus infinity. And these 2 boundaries are 2 halves of this sphere. So you can, by a conformal transformation, you can glue these 2 boundaries. So that at the end, by a conformal transformation, you can recover the single boundary description of this spacetime. Okay. So this is more or less the picture. You get global ADS with these 2 boundaries. Every boundary is conformal to half of the sphere, and you can think them glue these two halves of the sphere glued by the boundary. So you get something like a wormhole with only 1 boundary. There is a subtlety. This subtlety is that actually this that the 2 ADS3 boundaries are in a different equivalence class than the boundary with the sphere. Yeah, because they are connected by a singular conformal transformation. So they are actually not the same. So they are locally equivalent, but they are globally. You will get different results if you study, for instance, probably a CFT in one ADS3 and the CFT in the other ADS3. You will have different results than you study the CFT in the sphere. In particular, there is something that if you introduce this identification in U, it's not clear how to introduce this identification in the sphere. Okay, because the change of coordinates between the sphere and ADS3 are extremely complicated. So one is really in the practice when you introduce this identification, you are more or less obligated to work in the ADS3 coordinates, with the possibility of matching with having in mind that you can match this with another boundary with the other half of the sphere that is connected through the boundary of ADS3. Okay, now let's pass to the non-constant curvature case. So now we want to satisfy this condition, that is the condition where you are outside the topological censorship, but for a more complicated geometry. So we have these ansatz that respect the same symmetry than before, and we can see that this geometry actually satisfies this condition. So we are again outside the hypothesis of topological censorship, and one can this have integration constants. Okay, so this have sigma and m are integration constant. When sigma is 4 and m is 0, you recover the previous case. But in general, this is a different metric and it's not constant curvature. Then you can choose this parameter m and sigma such that f never vanishes. So you again have like interpolation between two ADS3s, but now it's not really between two ADS3s, but between two boundaries. And you want to see, and this geometry is everywhere regular. Okay, it's an everywhere regular geometry that interpolates between two boundaries. So now you want to see whether these boundaries are connected and whether this can be also made supersymmetric by embedding this in some supergravity theory. So I will pass to discuss this. And there is this very important thing that because there are no singularities in this space-time, in the bulk, for this geometry, then this set of coordinates provide a global covering. You can cover the spacetime with one patch. This means that time-like geodesics can be described globally by these coordinates too, and a time-like geodesic in general will satisfy this condition. With this, you can quickly prove that this time-like geodesic cannot be closed, because if it's closed, this means that there is a point where time starts going back. So dt, the zeta is 0, but when dt, the zeta is 0, this stops being time-like, it's space-like. So the geodesic cannot be closed and time-like. So it's a very elegant proof that this is causally well-behaved space. So let's pass to study the boundary. The boundary has this form. So this is people will be some people will understand that this is warp ADS. So now this is no longer the boundary is not ADS3, but it's warp ADS3 because one of the integration constant go in front of the fibration over the ADS2. So if we go to the coordinates where this is covered by the spheres, you will get something like this. So you can see when sigma is 4, of course, you get rid of these extra terms because you get something like the sphere times these other terms. But in general, this is not locally a sphere times R. So it's a very different spacetime. Actually, the spacetime is far from. So it's very far from being a compact space in general. Not only every slice, but also like the whole two boundaries. You try to glue them together, you cannot. You can compute the Riemann tensor, and actually you can see that, well, if the diagonal component of the Riemann tensor are constant, but this non-diagonal component is non-constant. This is a signature of something called a parallel propagated curvature singularity. We shall discuss more about this in a second. And this is existence of a parallel propagated curvature singularity in the boundary of ADS3 seems to indicate that it's impossible to transfer information from one of the boundaries to the other. This, of course, doesn't happen when the spacetime is not warped. When the spacetime is not warped, this constant is 0. So this term doesn't do nothing. If you try to use the same conformal factor than before, and see if this will generate like a well-behaved spacetime, a compact spacetime, you can easily compute that the Ricci scalar will be divergent. So when you use the same the same conformal factor than before, you can see that the spacetime is even worse than if you don't use it. And this already has been noticed in the literature by these people. they say that they claim that this spacetime doesn't have, warp ADS doesn't have a conformal compactification. So you will never be able to glue these two boundaries into a single boundary by a conformal transformation, which is the opposite of what happened when the boundary is really ADS strict. So now to study the supersymmetry of this spacetime, we need to come with a supergravity action. This is n equal to, this is gauge n equal to supergravity. These are the supersymmetric transformation. And the condition for this to be supersymmetric is that the variation of the gravity is 0. This is the condition. And typically, when you try to find supersymmetric solutions, you don't really solve these Killing-Spinor equations, but you solve the integrability condition. That is this, but we also we solve both, because since we make this identification, we need to be sure that these Killing-Spinors are well defined globally. So we solve these integrability conditions over the Killing-Spinor equations. Actually, this is we combine these chiral spinors into Dirac spinors to write this integrability condition as acting on a single spin. So because then we can put it in the computer and it's more easy to work it out. Then we extend our solution to the Einstein-Maxwell theory. So we have to put a gauge field. And the determinant of the integrability condition will give you just a function times this object, that is a polynomial in R. So you need to require that every coefficient of this polynomial in R is 0. Each one start giving you conditions on the integration constant. So at the end, you find that when this is something like the magnetic charge is equal to this in terms of this sigma that controls the warping at infinity, and when the mass is equal to this, you will get something. You will get a BPS solution. Then and from here you can see that sigma has to be bigger than 4, and this is important from something that we will have to discuss later. So when sigma is bigger than 4, is one of the conditions to be supersymmetric, and the other is this, that the P is equal to this and N is equal to this. These are the Killing-Spinors. So we were able to construct explicitly the Killing-Spinors for these non-trivial geometries. They don't depend on U, so they will exist whether U is compact or not. These are the explicit functions on U. This is the time in the y-axis is the time that a geodesic takes from going from minus infinity to plus infinity. So in connecting these two boundaries, it changes and it has a minimum for ADS and for ADS is this point here, and then if you start increasing the value of sigma or of the value of the electric charge, this is start always increasing. This is the embedding of the embedding diagram of this wormhole when we eliminate one of the non-compact directions, and so R is in this direction, U is the circle, and of course we have eliminated time here. So these are for two different values of this Q and sigma. There is this. You can see that there is more than one minima here, because it's a quartic polynomial. So it's like actually here you can see this quartic polynomial is this shape here along the throat of the worm. Then this is the boundary again. So this has 4 Killing vectors, this boundary, and so we can integrate the geodesic equation. These are you can get the velocities of the.
Andres, 5-minute warning.
5 minutes. So from the integration of the geodesic, one can find this equation, that is a relation between the velocity in theta and theta. And you can see that when lambda is less than 1, lambda is 4 over sigma. Okay. So you remember that sigma has to be bigger than 4 for supersymmetry to exist in this spacetime. So when sigma is bigger than 4, this is positive. So Q has to be bigger than L. But when Q is bigger than L, for large theta, L is always, this part is always negative. And because of this is always negative, then this means that generic geodesics in warp ADS3, generic null geodesics in warp ADS3 are confined. They cannot reach infinity. This is not true when Q is equal to L, but Q equal L is like a set of measures 0 in the space of integration constant. But so generic geodesics cannot reach infinity in warp ADS. When Q is equal L is different. When Q is equal L, you can reach infinity through this geodesic. So you can construct what is the tangent vector to this geodesic that actually reach infinity, and not that reach infinity while winding around you. So you go winding around you, you can go to infinity, and you can construct what is the parallel propagated Riemann tensor along this null geodesic, and then you can see that this parallel propagated Riemann tensor is divergent. This means that tidal faults are divergent when you go to infinity for geodesic observers. So this is typically is a signature that you cannot go through this point. This is however, all the components of the Riemann tensor in a static basis are well behaved. So this is only along this null geodesic that reach infinity. So it's like this is called parallel propagating singularity, and it's a very special kind of singularity. And what is very interesting is that it seems that nobody have noticed in the literature that this is this warp ADS, which is relatively well known in space-time, have this kind of singularity. Yeah. So this also have so to start ending this. Well, this is as a conclusion. We believe that these two boundaries in the warp ADS case cannot be connected through the boundary. Okay, this is our conclusion because of the existence of the singularity. And in the other case, when in the ADS3 case, we believe in the constant curvature case, we believe that the boundary is connected. When the cosmological constant is positive, you can construct some geometries that have the same structure, such that they are everywhere regular. They are asymptotically de Sitter, and all the coordinates are compact in this case, and they go to a minimum, but a minimum in time. So this describe bounces in the Sitter. So this is like the Sitter analog of these wormholes. And they connect two asymptotically de Sitter spacetime. So it's like this tunnel that Juan was talking before in his talk. This is like a realization of this, because like you have these two de Sitter slides that are asymptotically, and they are connected through a tunnel. And this is the interpolation between these two de Sitter slides. It can be found exactly. Here we can see that for this value sigma equal 4, you can really get that this is asymptotically de Sitter global. And we generalize this cosmology to the case when the bulk is also inhomogeneous, but with Jean-Luc Lenners and Sebastian Bramberger. So the future work is to keep studying the cosmological applications, to embed this, because since we embedded this in equal 2, we can uplift to 11-dimensional supergravity, to study this embedding, to study the spinning solutions of these wormholes, and to study applications in holography that some Italian friends are studying this already. Thank you.
All right, so I see there's a question by Eloy Ayon Beato. Please go ahead.
Hello, Andres.
Hello, Eloy. Nice to meet you. Nice to see you.
You can show again, please, the transparency with the charged solution.
Yeah.
Okay, thank you. Andres, this look like a sort of double weak rotation of the charged tau naught solution having an hyperbolic base. It is known that the tau naught solution preserves also a part of the supersymmetry. Can you comment a little about that?
Well, yes, this is locally a double weak rotation of the tau nut ADS tau nut. But then you need to so actually all these solutions are like special cases of something called the Plebanski-Demiansky solution that contains the most general Petrov type solution in 4 dimensions. So what we did is not really to find a new solution here. What we did is to take one case of this solution who was not being looked with care. Okay.
Okay.
This can be seen as a double weak rotation of hyperbolic tau nut, and the problem with hyperbolic tau nut is that it has closed time-like curves because this vibration here is time-like. And when this vibration is time-like, you go in a lot of troubles. But because this vibration here is space-like, you don't have any trouble. You see, this is the magic.
Okay, so I think it is important to mention that, no?
Yeah,
because this result the importance of the work that you did. So, okay.
Okay, yes, but you're right. This is can be seen as a double weak rotation of the CETA ADS tau nut with hyperbolic
base. Thanks, Andres.
But here, and yes, actually this is very interesting because tau nut is typically very pathological, but because of the vibration is space-like, you get rid of all these pathologies. This is the same.
Okay, very nice.
I don't see any other question. Okay, Carlos Núñez, please.
Sí, give me a second. Andres, one question. Tell me if I understood. You are finding here solutions that go from some warped ADS to an ADS3 to another warped ADS3. Is that correct?
Yeah, that is correct.
That is correct. Can you compare? So what's the ratio between the radiuses of the initial and the final ADS3?
Of the warpings?
No, of the initial and the final ADS3. So they come with a radius, right? How they compare?
They're the same.
They're the same. Okay. Okay. And another question when you lift this to 11 dimensions, did you study the integral of F4 in the lifting or F7 in the lifting?
I still don't do that, but
okay.
It's interesting.
Okay. All right. Thanks very much.
All right. So we have time. If you have any question, comment, as I said, we have time, please. So I do have, given Eloy's question, my understanding is that in tau nut, so you do have problems with the Misner string only when kappa is 1. So basically from spherically, but in your case, you don't have that problem, right? Because you are in a hyperbolic base. Is that correct?
Well, is that the Misner string appears because you, yes, well, appears because you want to construct everywhere regular space-time, where like some of the compact Killing vectors don't have have singularities. So you, depending on what patch of coordinate you use, you will have a Misner string in the south pole or in the north pole, which is similar to the Dirac string. Yeah, this actually, because of the coordinates are not compact, this doesn't happen here.
Can I ask another one, Andres?
Yeah.
If we have time, Leo. If not, we leave it.
Yes. There's plenty of time. So please go ahead. We have almost 7 more minutes for question. No problem.
Good. So tell me again if I am understanding. This ADS3 is the boundary of some ADS4, right?
Yeah, ADS3 is the boundary of ADS4 in this coordinate.
And you're finding a flow between ADS4 to ADS4, right?
Well, you find a flow. If you want to see this like a flow, you will see that this is a flow between warp ADS3 and another warp ADS3 in general, and in particular in the constant curvature case is about also, well, you can also make this warp ADS3 not warp, let's say. So then will be between ADS3 and ADS3.
did you see some solutions that, this is the question I have in mind, some solutions that Gauntlet had is Gauntlet, Rosen, someone else, that they are called boomerang RG flows, where he finds solutions from ADS4 to ADS4, right? Well, with interesting properties for the things he's interested on. This might belong to that class of solutions. He studies them in M theory, so you might be interested to take a look. Okay.
So he looked at like from 11 dimensions.
Yeah, he finds them in gauge supergravity in 4 dimensions, and then he leaves them. And this might be similar to the lifting you want to study, etc. Was just a comment about that. And that was a question about the integral of F4 that I had before, but okay.
Okay, thank you. I will look at that.
The title is Boomerang RG Flows, and it's Gauntlet and Rosen.
Okay, thank you.
All right, thank you very much. It looks like a good discussion that we can continue in a little bit. For now, let's break for 5 minutes, and at 2:01 we will resume. 2:01 my time, but I guess it's 1:01 Austin time.
Thank you.
Thank you. Thank you again. All right, Ricardo.
Hey, can you hear me?
Yes. Gusto verte.
Mucho gusto, Leo.
All right, so our second talk is by Ricardo Spindola. He will tell us about eternal traversal wormholes in ADS4. Go ahead.
Okay, thank you so much for the nice introduction, Leo. And also thank you to all the organizers for letting me to talk about my work in this beautiful conference. So I'm going to talk about some work in progress with a couple of students, Susana Ventaña, master's student, Dora Nicolacopoulou, PhD. We're working under the supervision of Ben Freivogel in Amsterdam. So wormholes. Wormholes have like a very huge literature coming from all the way from science fiction to very precise definitions. But very recently, some new interest has risen in study traversable wormholes in the context of holography, and also much more recently in studying traversable wormholes in the context of the information paradox problem. So all these constructions have like one precise origin, or there's one precise concept that lies in the origin of all this construction is the average null energy condition. So the average null energy condition is given by this expression. So given a stress tensor, you can compute this integral along some null geodesic, and well, k mu is just is a null vector. So the average null energy condition prevents for creating some shortcuts in space-time, like when you have 2 points that are close to each other in the ambient space, and the distance between them is shorter than the distance between the true wormhole. That is a shortcut. And if you impose the positivity of the average null energy condition and Einstein's equations, you prevent those kind of geometries. Also, it is known that classical matter satisfies average null energy condition. In general, it is very hard to prove, but it is conjecture that to be true. If one wants to create some traversable wormhole, then one needs to violate the average null energy condition using some quantum fluctuations. In particular, in holography, you can see these quantum fluctuations as some kind of Casimir type effect, given that the ADS space is like a box. So in recent years, Gaudio-Ferris and Wall proposed this traversable wormhole solution by turning on some double coupling at the boundary using the dual operators at the conformal boundary. So importantly, this type of wormholes are open only for a short period of time, the amount of time that you allow the coupling to be turned on. There are other types of wormholes. Those are eternal traversable wormholes. This was nicely described by Juan at the beginning of the session. This is obtained. This is an early ADS2 solution obtained by imposing a double boundary deformation as well, and the dual of this type of geometry was studied in this paper by Moldacena and Kim. Now there are other type of solutions which are D equals 4 traversable wormholes. These are asymptotically flat. These were studied also by Juan, Milekin, and Popov, and these are wormholes that far away from the mouths, they look like near extremal black holes, and they are threaded by some magnetically lines. Very importantly, they gave us the playbook that we are going to be following in all our discussion, because our motivation is, if there exists some D equals 4 eternal traversable wormhole that is consistent, because when you compute traversable wormholes using the Gaudio-Ferris Wall prescription, you need to find the stress tensor that will violate the average null energy condition, and then you need to back react the geometry. And as a result of that, you will have a eternal traversal wormhole. So I think it's a valid question whether this kind of geometry exists or not. Okay, so the idea is very simple. We have like 2 copies of CFT3s, which each one of those are holographic. So they have they lie at the boundary of some ADS4 spacetime, and we turn on some non-local coupling in the boundary of ADS4. Then we just need to find what is the stress tensor, and then solve some classical Einstein's equations. As a result of that, we should get some traversable wormhole, which is asymptotically ADS4, with some lines of magnetic flux, very similar to what Juan discussed with Milekin and Popov. Now, what is the system that we have in mind? It is some Einstein-Maxwell theory with some massless fermions propagating in the bulk. So this is the action, and as a solution to this action, it is well known. It is the Reisner-Nostrum ADS with some fermions propagating in this geometry. But since we are looking for a traversal wormhole, we are looking for a geometry that has no horizon. So we can use this we can use these conformal ansatz to try to get what is the stress tensor. So the dynamics of these fermions is given by the Dirac equation, and the important part of physics is that when you stay at the lowest lambda level, these fermions develop some they have some zero energy in the S2 geometry, and you end up working basically with some massless 2D fields in the bulk. Okay, now what are the boundary conditions? So usually the ADS-CFT dictionary states that some bulk Dirac massless spinor that is dual to a spin 1/2 primary operator, which it has dimension d equals 3/2 for the massless case. Now you need to you need to identify what is the source in the BEV. So the dictionary states that or the prescription says that you need to split into the chiral positive part or chiral negative part with respect to the radial gamma matrix. So, and then you, in the massless case, you can decide which one of the 2 modes are like the sources. If you turn off the sources, then you end up with reflecting boundary conditions for your fermions. Now, if you think on the 2-sided case, that is, you have 2 boundaries, right and left, the CFT the CPT boundary conditions for the right fermions imply if you turn off the source in the right boundary, the CPT conjugate then turn off the left source in the left boundary, and then you have vanishing stress tensor. This is a nice starting point if you want to perturb a little bit the geometry and then create some amount of negative energy. So that's what we use as a starting point. And then we introduce this deformation. This is the double deformation that we introduced. These are just the usual usual mass terms that you need to add to the action in order to have a well-defined variational principle. And then you add the double trace deformation here, proportional to h. Importantly, this double deformation is valid for all values of time. And as a result of this deformation, we have some modified boundary conditions. So if you turn off h, we have again the CPT deformation, the CPT boundary conditions. Now with h different than 0, we have these 2 set of boundary conditions. This when you solve field equations and you quantize your fields in then you restrict to the lowest lambda level so that you have only 2D effective spinors. You can compute what is the spectrum of those wave functions, and you have a slight perturbation away from the original. And then you can also have like a 2-point function. You can compute also the 2-point functions that are also modified. They are proportional to this h. And due to translational invariance along x and t, you have this difference. Now that you have the modified 2-point functions due to the modified boundary condition, you can compute what is the stress tensor in this theory, because we want to violate a little bit the average null energy condition. So we use the formula of point splitting. So given the 2-point function, we can compute, and taking the limit when when one of the 2 points goes to the other one, you can obtain the value of the stress tensor. In general, these stress tensors are very complicated to obtain in higher dimensions. They are usually divergent. So we were able to compute a finite stress tensor that has this form, is proportional to the double deformation at the boundary. It is zero along these directions because we have spherical symmetry. And now the game is to try to backreact the geometry and solve the semi-classical Einstein's equations. The stress tensor now has 2 pieces. One is this magnetic black hole and classical magnetic black hole, and then we have the contribution from the fermions, from this quantum theory. So as a result, in linearized perturbations of this deformation, we get in the throat region some slight deformation of ADS2 crosses 2. As you see, if you turn off these 2 perturbations, gamma and psi, this is just global ADS2 crosses 2. And once you turn on this deformation, proportional to h, you have a non-zero profile for these psi and gamma functions. Importantly, you obtain 2 second-order differential equations in order to fix the integration constants. You should impose C2 symmetry along the origin, because you need to have in mind sort of the strip of ADS2, and we have a radial coordinate going to the right boundary and another boundary to the left. Okay, imposing C2 symmetry, you get you fix what are these fluctuations. Now, as you start going away from the throat region, the magnetic stress tensor starts dominating more and more. So for large radii, the magnetic stress tensor dominates, and then you expect that far away the solution will be the Reisner-Nostrum black hole. So far away, the geometry looks like this. And as rho increases, the linearized fluctuations also increase. And we expect that at some point, as we are going away from the origin, or we are approaching the mouth of this wormhole, we will smoothly interpolate to the Reisner-Nostrum geometry. So we expect that, or say in the other direction, if you start with the Reisner-Nostrum black hole, and then you go to the near horizon expansion in this form, where epsilon is just tells you how far from extremality you are, how close to the horizon you are, then this geometry should match with the other throat region. Okay. Now, the gluing. So close to the throat, we have some deformation of ADS2 crosses 2, which has rho and t coordinates. Far away, as we are going away from the origin, we smoothly interpolate to this Reisner-Nostrum black hole far away, and this is done by this change of coordinates. This is the dictionary between the coordinates in this ADS2 crosses 2 region and the coordinates in this radial nostrum radius for black hole. Importantly, there is an overlapping region between the two, given what we just discussed. You start going away from the origin, so you need rho to be very large, and you can do that because you can consider h to be very, very small, or maybe you can work in finite h, but gn should be also very, very small. And you need to be also in the near horizon regime, where this expression is valid. This is just telling you how close to the horizon you are. And importantly, we identify what is the cutoff until when the solution is valid in the throat, and it has this form, is proportional to h. So all this solution is possible due to the double deformation that we have. That we
1-minute warning.
Yep. Now, just to finalize, I want to give some more aspects of this solution. We also studied the nonlinear Einstein's equations, and we can write them in terms of just these 3 independent parameters. And once you fix all these 3 independent parameters, there is a unique solution. There is a unique wormhole solution that it is well behaved numerically. Importantly, I said that we turn on this double deformation for all values of time. That means that this wormhole geometry is stationary, and when we compute the mass, there is a slight decrease in the mass. So what it means for an infalling observer, this is like super funny. You are far away from the mouth, and then as the infalling observer is going towards the mouth of the wormhole, he sees that he's going to fall into a naked singularity. But when he is approaching the throat, then when he's approaching the mouth, the throat all of a sudden opens, and he goes smoothly into some near ADS2 cross S2 geometry, some global ADS2 geometry, and then he comes in the other side. So just finally, there are still some things that we would like to discuss about this wormhole solution. What is the actual CFT dual understood from the point of view of the Hamiltonian point of view? So there should be some. So we would like to say that this geometry is actually dual to the ground state of this Hamiltonian. This is Hamiltonian studied by Diego and Ben. This Hamiltonian uses okay. Yeah, what's the name of it? So if you have a system which thermalizes, then the geometry, they studied that given the right and the left Hamiltonians, and they are coupled by some kind of term like this, what are the properties that this type of Hamiltonian should satisfy in order to have as a ground state a thermal field double state? So we expect to have some kind of story like that. It is also interesting to understand what is the relation with the ground states that were defined in these 2 papers, and also the relation with condensed matter systems, because they use some spinors in Kerr space, but in some radial nostrum backgrounds, and they model some superconductors. So given this geometry, what are the novelties, or what type of condensed matter physics we can learn? We will also like to learn about teleportation protocols, and more recently, as Juan just explained, it is quite hard to understand higher dimensional wormholes. So we would like also to understand these replica wormholes that are the ones that enter in the black hole information paradox context. Yeah, thank you so much.
All right, thank you for such a nice talk. So let's see what questions we have. I see Juan Pedraza has a question. Please go ahead.
Hi.
Hey.
Have you studied if there is any bound on information transfer between the 2 sites, or can you send arbitrary amount of information without this solution collapsing?
Yeah, we haven't studied still any kind of geometry through. Sorry, we haven't studied sending any kind of matter through the wormhole yet. Yeah, so that's still that's a nice question that we still want to explore. Yeah. Actually, the stability of this solution is also that we would like also to explore a little bit. There is also another story about superconductors when you have like so-called neutron stars. We would like also to understand if there is some kind of phase transition between those and this type of geometry and the disconnected phase, things like that. In this case, this will be like monopoles sitting in the geometry.
Okay, thanks.
So any more comments, questions? Carlos Núñez, please.
Ricardo, a short question that I missed when you said it. I got distracted and I missed it. You said that, okay, so you have the solution that is Reissner-Nordstrom ADS4 black hole going into nearly ADS2, yes? And when you patch these two solutions, do you need to add any extra matter in the place where you make the connection between them?
Let me show you the slide where we do the matching. Here it is. No, this matching only relies in taking the usual Reissner-Nordstrom geometry far away from the horizon and then expanding close to the near horizon in this epsilon expansion. So far here, epsilon is just a parameter that tells you how close you are to the horizon, and then you simply match the two geometries, like the radial coordinate and the time component, and you simply realize that epsilon goes like with h. So
okay.
In some sense, you don't need to put any other matter in the theory, but it is due to the double.
If you try to match that's about the metrics. Very good. If you try to match the derivatives of the metric, do they match also the first and the second derivative of the metric in this case? Because those things are the ones that would indicate you if you have to put there some object, right? There are these, they're called in the name of matching conditions. Never mind if you're not aware, but that I understand that you can match the metrics.
You mean like
no
the
problem.
junction conditions?
Tell me again.
You mean like the junction conditions?
Yeah.
I think all that is fine. Yeah, I think if you compute the extrinsic curvature between the two, there is no kind of.
There is no object that you have to put there. Okay. You had a final comment there that this I missed completely, that you said, and we then solve the full Einstein's equations. How was that? So you are able to find the full solution, or solution all along?
Yes. So in the linearized problem, we just there are 4 Einstein's equations, and it's pretty simple just to get 2 second-order differential equations, and we can solve them, and we have analytic control on that. Now you can ask the question if you can solve the nonlinear Einstein's equations, the 4 nonlinear Einstein's equations, and just playing with equations. There is just one constraint equation. Okay, maybe I should tell you the ansatz that for which we solved is this one. It has 2 independent functions, so sigma and r, and they depend only on x. Now,
and also, Ricardo, also you solve for the dynamics of the fermion, right? So that, that equation of motion will back react to the gauge field, and right?
Yes. Okay. So we are thinking that the gauge field is fixed because we are looking far away. We have like a Reissner-Nordstrom solution with some magnetic fixed charge, and then we solve for the fermions, and we go to the lowest lambda level, And in the lowest Landau level, these are just like free 2D fermions moving in like in the strip, for example, in ADS2. And and then we compute the 2-point functions, the stress tensor out of those 2-point functions, and then back react the metric. Exactly, that's what I'm saying, that it is not immediately obvious that all this process is self-consistent, because we start with some geometry, and then we solve for another wormhole geometry with the source of stress tensor. So in that sense, there is no matter is traveling through the wormhole. Yeah, thank you.
So maybe I'll ask just about this approximation. So you compute the 2-point function and the stress energy tensor, but that is independent of the metric, right? So when you look at the Einstein equations, again, you're assuming that your stress energy tensor is what it was before. It is not now depending on the metric in any way, right?
Indeed, yes.
All right, any other questions or comments for Ricardo?
I can comment a little bit on that. You're absolutely right.
Yes, please.
So the stress tensor. So we compute everything like in the linearized approximation, and we get this stress tensor. And once we put it in the Einstein's equations, it is the question of if we manage to have like a stable nonlinear solution, right?
Mm-hmm.
So if the only approximation I think we make is here. When you consider like H to be small, but you can also consider like, the stress tensor doesn't care really that much about all this structure, because you are just considering the stress tensor at a particular point of space-time. So you can say that you are in the regime where these 2 points are very, very close, and you can allow H to be finite. And if the spectrum doesn't have like a huge back reaction, you can have the same stress tensor. That's true. And we think exactly that the physical meaning, for example, of this square perturbation is due to what you just said. Even though we have some linearized approximation, we end up with something that hugely back reacts close to the horizon. So we were still studying if really we only need Gn, for example, to be small for this approximation to be true, and we can stick to, or we can work with finite H. Yeah.
All right. Thank you. So any other questions or comment for Ricardo? All right, so looks like we're now going to have a break until 1:35. That's a 7-minute break, and we will reconvene for a discussion of all the speakers of today.